Good morning, distinguished guests, ladies and gentlemen, and welcome to the International Workshop on Future Communications. My name is Wayne Chan, and it's my pleasure to be your host for this event. Now, information and communications technology has progressed significantly in recent years as a result of massive digitalization and the growth of digital economies. Now, Industry 4.0 has led to the rapid development and need for seamless interconnectivity among people and devices. Also, accurate location awareness for smart applications and faster computing solutions. Now, in this workshop, we will explore the technological changes that provided us a huge leap forward in speed, capacity, and connectivity, the challenges we face moving forward, as well as the efforts underway to consider beyond state-of-art protocols and mechanisms for wireless, data, and network communication. Now, over the next 2 days, we'll be hearing from 11 distinguished keynote speakers on the future generation of communication to meet new demands and challenges that go far beyond distribution of voice, video, and data. Now, this workshop would not be possible without the generous sponsorship of our sponsors, and we would like to take this opportunity to thank Anritsu Private Limited, Huawei International Private Limited, Keysight Technologies Singapore Private Limited, MediaTek Singapore Private Limited, MPix Innovations Private Limited, Quanta Computer Inc., Intel, Roder and Schwartz Asia Private Limited, ST Engineering, ST Microelectronics, United Microelectronics Corporation, and also the support of IEEE Communication Society and International Electronics Manufacturing Initiative. Thank you so much to our sponsors and partners. And now, to officially kick off today's event with an opening address, it's my pleasure to introduce Professor Kiat Seng. Now, Professor Yeo is an IEEE Fellow who is a widely known authority in low-power RF wave IC design and a recognized expert in CMOS technology. Ladies and gentlemen, let's welcome the Associate Provost, Research and International Relations, Singapore University of Technology and Design, Professor Kiat Seng.
Thank you, Wang. Distinguished guests, ladies and gentlemen, good morning, good afternoon, and good evening, depending on where you are. A very warm welcome to the 2022 International Workshop on Future Communications. I'm Kiat Seng, Associate Provost at the Singapore University of Technology and Design, in short, SUTD. To our overseas participants who may not be familiar with SUTD, SUTD is a modern, international, and research-intensive university. It is Singapore's fourth public university, established in 2009 to pioneer interdisciplinary education, research, and design innovation. This workshop focuses on future communications. Future communication is a complex network consisting of a wide variety of products, services, and systems. Coincidentally, SUTD's academic structures are organized in terms of what the world needs, which are products, services, and systems. As the future network will become extremely heterogeneous, it will need a multidisciplinary team to address challenges to wireless connection, spectrum share, as well as data fusion. SUTD interdisciplinary research structure enables it to lead research and discourse on future communications. With speeds of up to 20 gigabit per second and the ability to support up to 1 million devices per square kilometer, 5G, the latest generations of mobile communication technology, may already seem impressive, but 6G is set to take these capabilities even further. For instance, with 5G, it would take about 4 seconds to download a 2-hour movie. However, with 6G, it will only take just 1 second to download 150 hours of Netflix show. With wireless connectivity becoming increasingly common, there will be more applications like virtual, augmented reality, artificial intelligence, and even autonomous vehicles requiring high data rates combined with low latency or delays due to processing time. Accordingly, 6G, with its peak data rate of 1 terabit per second and latencies of 100 microseconds, should be able to smoothly support these use cases. At the same time, individuals and organizations will expect a trustworthy network that can seamlessly and securely deliver data, meaning that further research must focus on building a holistic 6G network security architecture. Since 2020, the standardization of 5G wireless communication networks and the simultaneous deployment across many countries worldwide is underway. Until the start of 5G communication, the network utilization was predominantly for the entertainment video and audio file streaming and buffering applications. One of the core distinctive benefits of 5G communication is the low deterministic latency to assure an end-to-end reliability and accuracy that future applications mandate. However, 5G networks consume more energy than 4G networks. This is because off-the-shelf servers are used against the application-specific integrated circuits in a radio access network. In disparity, we must target to deliver the next generation networks that at their introduction time does not surpass the previous generation energy needs. Therefore, the requirements of future networks should not be fulfilled just by merely using 5G. Hence, the focus has started on the research for 6G wireless communication networks. Recently, mathematical computing has developed variations such as cloud computing, fog computing, and edge computing. As these new variations are being evolved, new application scenarios utilizing them are hopeful to resolve some inherent network concerns, such as the network flexibility, distributed computing, low latency, and precise time synchronization. These are also some of the limitations of 5G caused by short packets. This restriction from 5G causes degradation of some of the requirements such as high reliability and low latency. Hence, 6G is bound to addressing some challenges application. 6G will likely be an efficient and self-contained ecosystem based on AI, which progressively evolves from being human-centric alone to being human and machine-centric. 6G will also bring a low latency and unrestricted complete wireless connectivity. Hence, enormous efforts are underway to consider beyond state-of-the-art protocols and mechanisms for wireless communication. Thus, the next generation of wireless communication is expected to meet the demands of various challenging use cases that go far beyond distribution of voice, video, and data. I'm therefore delighted to know that this international conference aims to discuss the open problems and present new solutions that address the challenges of future communication systems, such as 6G. Finally, I would like to thank our keynote speakers, conference participants, IEEE Communication Society, and our sponsors for their strong support. My special thanks to the conference organizer, Lin Chiu, and her team for putting together this wonderful program for everyone. Thank you and enjoy the conference.
Thank you so much, Professor Yo, for welcoming this year's participants. Now, for today's program, we have an exciting lineup of enlightening presentations. And coming up next, our first keynote of today is on the continuous innovation of wireless networks from 5G to 6G. Now, in this keynote, a roadmap towards 6G will be discussed based on our learning from 5G deployment, society's needs, and future technology trends. And to tell us more about all of this, I would like to introduce our first keynote speaker for today. She is an IEEE Fellow, a Huawei Fellow, a Canadian Academy of Engineering Fellow, and she was a Nortel Fellow and Director of Advanced Wireless Access Technology in the Nortel Wireless Technology Lab, who led the team and pioneered research and prototyping on MIMO, OFDM, and multi-hop relay, which have been adopted into LTE standards and 4G products. She also currently is leading 5G and beyond wireless research and standardization in Huawei. Ladies and gentlemen, let's welcome the Senior Vice President of Wireless Research, Huawei Technologies Co. Limited, Dr. Peiying.
Thank you, Yuen, for the nice introduction. Hello, everyone. I'm Peiying from Huawei, Canada. So my talk is on the continuous innovation of wireless network from 5G to 6G. So what I will do is I will first share with you some of the latest progress on the 5G and 5G advanced. Then I would talk about our view on the 6G. So you have here the 5G for the past many years now. In fact, even I have been working for 5G for quite a long time. I'm still quite amazed with the latest progress of 5G, especially for the commercial deployment. If you look at the those number in terms of number of commercial network and number of base station sites and the number of users got connected and the number of the type of devices, 5G devices on the left side, you can see those numbers are amazing. And right now we have consumer using our 5G and have a very great experience in terms of their EMBB usage, especially for the video and high definition video and the AR, VR type of applications. You can see the last year, there's more and more traffic actually shift from the previous generation of network to the 5G networks. You see the 43% of increase of mobile traffic, and also the there's a lot more 3 times for this mobile video traffic increase. And the other very interesting application is fixed wireless to home. There's actually there are many people actually benefit from this fixed wireless to the home. So in addition to this, on the vertical market, we have moving from the the theory or some trial testing to the actual commercial contracts. You see, last year we had 10,000 of innovative projects ongoing, and there's 4,000 contracts signed, and specifically there's some sector which we actually have the network working related to the the transportation side and the manufacturing side and the mining industry and so on. So with those type of commercial deployment, we actually learned a lot by looking at these actual applications. Specifically, we found the some new requirement and new use cases. So therefore, we have been looking at how to further improve or evolve the 5G networks. So for the past 2 years or maybe we have been looking at how to create the new use cases which are neither typical EMBB or UILC, but it's a combination of this type of use cases, such as a real-time broadband communication, where you actually need the low latency plus the high data rate. Similarly, for the vertical market, we see more and more requirement on the high-speed uplink capability. So we see the uplink-centric broadband communication, such as this high-definition video uploading or the industry machine vision type of applications. And we also see the need of this positioning and the also vehicle type of application related to the positioning and the sensing to understand the, especially for autonomous driven car, you need to understand the environment and so on. So we see those new usage type of scenario pop up. So that's the vision we see for moving the 5G toward the 5G advanced. Now, this vision is no longer, the requirement discussion. Rather, we have already started the standard discussion. So for the release 18 starting this year, we agreed to start this 5G advanced study item or work item. On the right-hand side, you can see the those are some of sample of this agreed work item or study item. For example, we will have enhancement of MIMO side, considering that we may have a new mid-band, like up to 6 gigahertz band, possibly for use. These are actually allow us to do even wider band and also more antenna. And also we're looking at the uplink enhancement to include a better MIMO support and more flexible use of spectrum, so that we can actually dynamically shift the capacity from downlink to uplink, or uplink to downlink to suit the needs. Then, of course, I mentioned that we see a lot of demand for the AR, VR, and XR type of applications. And with this, we want to be able to support more users in cell. And so we are looking at how to natively support this application, utilize some features in the coding, so that we can get a better QoS support and so on. And also we have this reduce the capability type of devices, so that we can better support the IoT market. Then there's some enhancement to allow us to use the multi-carrier efficient. I mentioned about the positioning, so there is a work item on the improve the positioning, including the low power positioning, and the network energy consumption. This is the key in everyone's mind. So we have work to further reduce energy consumption. Then there's also AI and machine learning type of application. This I will talk a little bit later on to show you a bit more on what we are doing. There's other item as well. I'm not listed all. So we expect that we will have a 5G advanced maybe in release 18 and release 17 and release 19. Then after that, probably we will start to looking at the standardization of 6G. So with that, we talk about there's a lot more we can offer with 5G and 5G advanced. So what more we can do with 6G? So there are two major things we see driving us to look toward the 2030 and beyond. One is the advancement of the AI technology. Then the other one is we see the more and more device with intelligent capability. So, for example, we see the advance on the robotic industry, and we expect that toward the future we will have these robots serving people and serving the society, and they need to be connected. So we really see the shift from the early generation of connecting people to the 5G. We start to connect things, and the 6G we probably will actually connect the intelligence. So the 6G in the high level, essentially we are looking at the beyond the connectivity capabilities. Of course, we will continue to improve the communication connectivity. So if you look at the definition of 6G, in 5G we actually have the typical 3 usage scenarios, which everyone know by now. We expect these envision the service will be continue to be improved, enhanced. We will have a 6G serve them better. So we labeled them as plus. Of course, I already mentioned even 5G advanced. We are looking at the combination of these scenarios. This will happen in 6G as well. But on top of that, we see that with the introduction of the higher frequency band or the more antennas, we actually can use our communication system for the sensing as well. So we introduce the new sensing capability, and on top of that, we want to use our network as a platform to offer the AI as a service. So this is what we call the network AI. So these two combined with the other cases, we think that will be driving the design of the 6G. And of course, with those capability or usage scenarios, you can see there's lots of use cases we can actually, or applications, services we can offer. I listed some of those here, but these are not exhaustive. It's just give you a flavor of what we can do with the 6G. On the high level, we see the 6G network in the future. It will have a different type of devices, and these devices not only have the communication capability, it has the sensing capability, and it has the capability to do the machine learning or AI. Then with those sensed data, we can either locally extract some features, or we can send the raw data to our base station. We here, of course, our base station have the sensing capability and learning capability as well. So we in this diagram we called it the neural edge, but basically at the edge we're close to the user. We will do some further study or learning. Then the finally we may need to send it to the cloud to do the fine tuning. And with this type of system, we can actually build a replicate of the physical entity in the cyber or virtual world. Then many actions can happen with these models. So we can perform many actions. Then once we are happy with the actions, then we can send back the action to the physical world, actually get the actual results. So so you can see with this type of network, we're able to fuse the physical world to the virtual world, and make the people are also talking about the digital twin, metaverse, and so on. But this in that direction, we can offer many services. So in terms of spectrum, people you probably hear people talking about the terahertz for 6G, but we believe that. In fact, terahertz is not going to be the major spectrum for 6G, but terahertz will open some new applications such as sensing and imaging. But we still need the low or mid band so that we can have the general coverage, and also we think the millimeter wave we introduced in the 5G, but with the technology mature, towards 2030, so we probably will use more in 6G. Then one of the major thing we're actually now looking is what we call the centimeter wave, somewhere between 7 gig to the 26 gig. This area, we think that will be if we can find a global band for 6G, that will open up high speed data transmission and wider coverage and so on. So in terms of 6G capability, we see the six major capability. The one is native AI support. Then the second is network, the sensing. The third one is extreme connectivity. The fourth one is the integrated non-terrestrial network. Then on top of that, of course, the trustworthiness and the sustainability are the two very important aspects as well. So I will explain a bit further on these capabilities, especially the first two ones, because they are rather new for 6G. Not that the other ones are not important; they are equally important. And also, if you are interested to look at the details, we also have a white paper you can take a look. So what do we mean native AI support? So there's two aspects. One aspect is that we use AI as a tool, optimization tool to improve the either link level performance or the network resource allocation or the network management. The second thing is really more interesting, is that we actually use the network we will build AI learning and inference into the network, so that network will be used as a platform to managing data, managing learning, managing interference, and so on. So if you look at this AI full network, then we already started this work in 5G. We have some work in terms of define the interface to collect the data so that we can better understanding how the network is performing. And also we have a new study item just I mentioned in release 18, we're looking at how to improve the link level performance. But this is assuming we use the existing 5G framework. Then we, some module level, we can optimize it. Then going forward from 6G, we see we want to build in day one so that we can utilize AI capability so that we can fully automate the network management. And also when we look at the AI interface design, we actually thinking how we can leverage the AI capability so that we can make the AI interface is self-learning, self-adapting. Then if we look at even further, I mentioned that we have the vision to connect the intelligent devices or machines. When these machines communicate with each other, if both of them have the AI capability, then we don't need to communicate the actually information bits. We can communicate some semantic level of the information. So those actually is more interesting aspect for 6G to look. So here are some example what release 18 study item are looking at. So one of the things is when we have the massive MIMO, we need to feedback channel state info. If we continue to increase the number of antenna elements or antenna ports, then this feedback channel state information actually consuming lots of bandwidth to feedback. So with AI, we can utilize this AI capability to do this type of compressed feedback, either to reduce the overhead with the same performance as here has an example. We can see we can reduce the overhead by 75%, or with the same overhead, actually we can improve the link performance. The second thing is for the beam management. In the 5G we have beam sweeping, trying to align which beam to send the data. But this process actually is time-consuming plus consuming lots of overhead and also the waste energy. So we're using the AI trying to reduce those complexity, and we actually see quite a success. So we're using some prediction. And also this positioning application as well. And there's discussion on how do we actually share the AI model. You can share the different level of informations. Going forward from 5G to 6G, actually we want to be able to not only looking at this model or share some parameters of model. We want to be able to sense the environment. Then based on sensed environment, we can build the maybe AI interface or adapt the AI interface accordingly. So I mentioned one of the interesting aspect for the semantic communication. So since we're envisioning lots of different sensors, so if we are looking at that we may have a different input source from a different sensor. Then we use AI to extract the information. Then we, of course, we need to extract the relevant information based on what you are looking at. Yeah. So this is what we call the goal-oriented filter. We remove the not useful information for my application, then send the remaining semantic information to the maybe a base station here or the network here. Then we do further processing, in terms of you have a different source and you have fused these results together, and also you need to look at the redundancy and also some of abnormal situation. So we're hoping that we can build a more generic framework so that we can, based on this framework, we can enable semantic communication. So that's the AI for network part. Then the other aspect of network for AI, 5G also looking at, there's a study item in the looking at this, how to support AI services. And the idea is we can actually use the current network, then the AI learning or the inferencing can this model data can just transmit over the using our existing network, but of course they have a different throughput requirement, different QoS requirement, and so on. But if you look at the results, actually, the requirements are quite diverse. Some applications require huge bandwidth or very low latency in order to make it working. So I think for 5G network, we can support certain applications, using the just network as a pipe or better pipe. But more important is that if we, for 6G, we look at the natively support this AI as a service, then we need to look at how to integrate the communication and the computing together so that we can do the federated learning or collaborative learning, and even we can based on our device or networks computing capability or some privacy concern and so on, we can have a better way of doing the split learning and so on. Of course, we want to be able to integrate the data management as well. So there's some KPI when we design the system, we need to take into consideration in terms of learning or inferencing efficiency, accuracy, and of course the power consumption as well. Yeah. So what we have in mind is that 6G, we have a distributed learning architecture. If user have the privacy concern or these data they don't wish to send to the clouds, then they can locally have a certain processing so that we can only transmit some intermediate data which are not reversible to the reverse engineered to the raw data. This also, if we want to look at the energy efficiency, if we move the computing closer to the data, we hope this will reduce the energy as well. Then similarly for the inferencing, if today if you have the cloud do the learning, then send you the models, you do the local inferencing. But if your device don't have this computing capability, we can actually offload the computing to the network so that you can do the joint or collaborative inferencing as well. And on top of that, if we want to do the multiple device jointly looking at the data from different angles, so those type of collaborative inferencing will allow us to build better 3D implementation. Yeah. So there's some implication on the RAN design as well. So the question is, how do we minimize communication overhead for those data and model transfer, and how do we actually aggregate the data together, considering the wireless links, the nature of a wireless link. And the same thing, how do we distribute this model? We have to think about this link is not reliable. This error will occur, and also the user is moving. Yeah? So you have to need to learn, be able to take this into consideration. So on the network architecture side, typically in the past we were more concerned on the connectivity. So connectivity is we typically have some session so that you can establish sessions, so you can have point A to talk to point, connect to point B. But if we're looking at this collaborative learning and inferencing, then it's not about this session anymore. It's about what type of task we want to complete with multiple nodes. So we need to think from session-oriented to the task-oriented design, and we need to jointly look at the communication resource and the computation and the data and this management together. So there's probably there's some implication in terms of how do we look at this protocol and the procedure as well. So that's the native AI part. Then for the network sensing, or integrated sensing and communication. So what we really looking is, our radio frequency. We can use the same radio frequency, hopefully same signal. We can utilize this for the sensing purpose. So this sensing is not only, we have today's network, we have a device, we can track the device position by device participating in this positioning procedure, but we are also for sensing. We are looking at the understand the passive objects like a building and surrounding environment. These building, are they not part of a device? Of course, they cannot help us to decide their position and so on. So sensing will do both of this device or device-free type of applications. And given that we use different frequency and we have a different deployment like a macro cells, so naturally we can do the multi-level for type of sensing with different resolution. So we can look at some parameters like position, speed, location, and so on. This is what we call the parametric sensing. But with even higher frequency, we can look at the imaging. You can actually build the imaging, even look at the image of hidden objects and so on. Then if you go even higher spectrum, then you can do the spectrogram. You basically, you can analyze the contents of objects. So if you look at the different frequency we have in mind, let's say for the mid-band or centimeter wave, like for example 10 gigahertz, or the millimeter wave, and the even higher bandwidth, you can see we can actually calculate, given a certain antenna size, we can calculate what kind of accuracy we can achieve for the either this parameters or the imaging resolution, and so on. So with this, we can actually use for the different applications. So with sensing, we can also use the sensed data to assist the communication, so that we can improve the communication performance. For example, if we actually sense the environment and build a digital model of the environment. Then with this digital model, we will be able to, use some type of ray tracing type of technology. You can actually decide where my coverage is, where should I put the, my base station, and where we should, send the beam, and so on. So here's an example. Like we have on the left side, this is our sensed data is point clouds. Then based on that, we reconstruct the model in the middle, the image. Then based on this construct model, we can predict the channel, and based on those predict channel, we can decide where we want to, direct our communication. So if you combine the AI and the sensing together, this will even create more business opportunities. So essentially, you have the sensing enable the network to see things, and the AI enable network actually to understand things. So it's joined together, we will be able to open new business opportunity. And with this, of course, we have the new KPI, as I mentioned, for the sensing, we need to think about the sensing resolution, sensing accuracy, and for the AI, we need to think about how to, the inference accuracy, latency, and learning efficiency, and so on. So that's two new things we're talking about 6G. And for the connectivity, of course, this is one of our key for the mobile network. We will continue to improve this network. I think I just heard the talk at for the introduction, talking about the very high data rate and low latency system, and we're thinking the 6G we can build 6G so that have the almost the fiber-like link performance, so that this will enable us to have a really immersive human-centric communication, such as multi-sensory type of application and holographic type of application. Then for the vertical industry, we see the 5G will enable many use cases, but there's also certain use cases probably beyond the 5G's capability. For example, we see the in the future we will have multiple robots to cooperate to complex to perform some complex task. This not only requires the low latency, maybe requires a very low jitter as well. And we also see the cobot type of application, like the human and a machine working together seamlessly. So of course, this you require better, data rate, user data rate, and low latency, and including energy efficiency, and so on. So so those are the traditional evolution of the wireless system. There's many technology we are exploring. For example, for high frequency, we are looking at how to build the high frequency millimeter wave network so that you can improve the coverage, and you can even perform the continuous to avoid the obstruction and so on. Then for the telehertz, this is a brand new area that we're looking at every aspect, from device to the actually protocol design and the signal like waveform design and so on. Then this possibility, we can even use optical wireless for certain applications, especially for area where we are sensitive to the IF radio type of signals. So like a hospital, you can use those. You can do this very high speed, and with MIMO, we say we already doing this many innovative massive MIMO solution, but going forward with centimeter wave bands, we can actually utilize even more high order MIMO. So that there's a lot of innovation in this area. Then of course in the arrays, and we were looking at whether we can use this to reduce energy consumption. There's some OEM technology, especially for millimeter wave. This possibility we can further improve the efficiency of the millimeter wave. So then there's fundamentally this coding waveform and modulation and this technology, including the full duplex technology. So in terms of non-terrestrial network, 5G already started working on the to support the non-terrestrial network satellite. And we have done some testing, and we actually can prove that with NI design we are able to do the satellite communication using the NI, some slightly modified NI interface. But going forward, we actually looking interested in the very low video type of satellite communication, directly talk to the mobile. And we want to be able to integrate this seamlessly with our terrestrial network, so that the user can benefit for the both system, especially for the rural area. And also there's one aspect is once the satellite is at very low height, then it becomes very interesting actually for the long haul type of communication. Using satellite will be provide a lower latency than the fiber. With this, we see this possibility. We do the autonomous driving, especially in the rural area, and also the we see the expand the coverage with the support of non-terrestrial network. Of course, we not only looking at the satellite. There's also work related to use the drones or the HAPS type of, or even flying bus and those type of devices. Yeah. So the native trustworthiness is that we already start to see the ecosystem in terms of the network operators actually become more diverse. Like 5G, we now have a public network and also a private network, which could be run by the non-traditional operator, or could be run by a traditional operator as well. But going forward for 6G, we see the ecosystem will be more diverse. So this poses a challenge in terms of how do we actually build such networks so that it's you can actually really make sure it's trustworthy. So there's 5 different aspects in terms of what's the trustworthy. You have the safety, reliability issue, security, privacy, and resilience. Product implementation aspect. So we're looking how to build this from the traditional network, in the sense we mobile subscriber trust the mobile operator. So we build this type of trust model. We're moving this toward maybe how do we build trust within multi-party, so that we can have a multi-party consensus model, or this third-party endorsement type of solution. So those are still under the research, but on top of that, there's also, we need to think about by 2030, there's a possibility with the advance of quantum computing technology. We need to think about how to make our encryption so that it can combat with this quantum type of malicious attack. So we're also looking at maybe physical layer one-time pad key, this ultimate security mechanism. I talk about the multilateral trust. There's a possibility we can utilize some blockchain type of technology to enable us to do this type of trust mechanism. And I mentioned also this, we could use the quantum distribution, key distribution solutions as well. So in terms of sustainability, in fact, this is the top priority on every operator's mind. There was a survey asking the operator whether they think this power consumption or the carbon neutral. These are the important issue or top priority. Almost 95 or 99% of people think that's the key. So if we look at for the 6G, if we think about we're looking at the AI, deep learning, and this will actually consume even more power. And if we move to the high frequency, and also the power efficiency is not that high, so we need a new technology to actually to combat these issues. We're looking already in the 5G. We're looking at the different solutions to minimize the power consumptions. So for the 6G, on top of that, we also need to pay attention to the low EMF transmission technology, because there might be a restriction, actually regulatory restriction to cap the power, transmitted power and so on. So we also need to have a better way of evaluate this, what we call the sustainability. So all this technology, we have been working on this for several years. There are some prototype we built to prove the feasibility of certain technologies. Here are some of example. We have this integrated sensing using terahertz, and we have the also using integrated sensing for the terahertz transmission, and the with optical wireless. We use this for the health application and positioning. And also we have some extremely low power, high speed. This is trying to enable the XR applications. So yeah, welcome to look at our website listed below. We have the video, and we have some explanation, some paper to further explain all this technology and what we some of results. Of course, we cannot do this alone. We need to have a collaborative effort to define the 6G. So right now, actually, as I'm speaking this week, ITU actually have this meeting to look at the 6G vision. There are 6 usage scenarios currently being discussed. Similar to what I mentioned before, and also there's some user application trends and so on. So we probably will issue this report by mid of next year. There is also a report will be probably completed at this meeting for the future technology trend, and also this work on the channel, the feasibility study for the frequency above 100 gigahertz. So in summary, we see 5G is progressing very well. This will give a better user experience, and we better support the industry. And we see the 5G advanced is being standardized and will support more use cases. And for 6G, the main thing is that 6G will go beyond communications, and they will become a platform to support the learning and sensing, and with the following mentioned 6 key capabilities. And we believe that a global 6G standard is the key to the success of 6G. So we see the industry consensus are being building up. Okay, so I will stop here. In fact, if you needed to look at even further details on the 6G, we have a published book last year. This is available, so you're welcome to take a look. Okay, thank you very much. I will stay on for any questions.
Thank you so much, Dr. Chau, for that interesting presentation on continuous innovation of wireless networks from 5G to 6G. And now we're going to move on to our question and answer segment. And we have our first question right over here. And it says, how, according to you, COVID-19 pandemic contributed to the development of new wireless technologies? This question is from Shemuel. Thank you for your question. Dr. Chau, what are your thoughts on this?
Yeah, actually, I think this our 5G system definitely played a significant role for the pandemic to enable people to still stay connected, to be able to learning, or even more importantly to be able to get the medical services remotely. I think there are actually some trial doing the remote diagnose, even some remote operations view our 5G network. So I think this, of course, you see this virtual meeting stuff definitely have lots of requirement, pushing the higher capacity of the network and so on. So I think this definitely changes the way we live, and I think this we are actually looking at the 6G, where we're thinking, today we have the video conferencing. If in the future we actually be able to offer this platform so that you can feel the presence of the other party, maybe this will even better. Yeah? For the our aging society, if you can actually enable the remotely give your parents a hug, or even kiss, this probably is very good for the society itself as well.
Thank you so much, Dr. Chau, for
Thanks.
the answer. Definitely looking forward to those remotely delivered hugs and kisses. One more question over here from our audience, and this question is, what are your thoughts on applicability of quantum communicability in 6G? What are your thoughts on applicability of quantum communicability in 6G?
Okay, so I think when I talk about the trustworthiness, I mentioned about the quantum key distribution. I think this technology is relatively mature comparing with the quantum communication itself. So I think that might have some application in 6G, but quantum communication itself, I'm not sure. Actually, I think that may be even more less mature. Maybe we can look at it in 7G. I'm not sure actually this.
Thank you so much. No worries. We have time for just one last question, and the last question that we have here is 5G's just started to be deployed. When do you think that 6G may start to commercialize? What do you think?
Okay, so from our perspective, we think that we have the 5G now. Then by 2025, maybe we will have the 5G advanced. Then around maybe 2030-ish, we will have the commercial deployment of 6G. But there's also some other, company or country. They think that 6G commercial network will start even earlier than that, maybe around some test version of 6G, maybe around 2028, 2029. But I think we basically need to learn from 5G. This vertical industry and all the non-traditional communication network take times to be able to adopted by other segment or other sectors. So we need some time to make sure we get a 5G system, for vertical application to be adopted first. That's why we want to give a little bit more time to the 5G. Yeah.
Thank you so much, Dr. Chau, once again for helping to answer all our audience's questions, and of course for your exciting presentation on continuous innovation of wireless networks from 5G to 6G. Thank you so much.
Thank you, Yuen, and thank you for the audience to listen this as well. Yeah.
And now, the topic for our next keynote is AI-assisted reconfigurable intelligent surfaces wireless networks. Our next speaker will present some recent results on the reconfigurable intelligent surfaces wireless networks empowered by AI. In particular, a deep learning-based hybrid beamforming for RIS-empowered multi-hop terahertz communications, AI-assisted MAC, and intelligent spectrum learning with RIS. Now, our next speaker is an IEEE Fellow and Distinguished Lecturer of IEEE Vehicular Technology Society. He received the IEEE Marconi Prize Paper Award in Wireless Communications 2021 and serves as an editor for IEEE Transactions on Vehicular Technology and IEEE System Journal. Now, since 2010, he has been with the Singapore University of Technology and Design. Ladies and gentlemen, let's welcome Professor Yuen Chau.
Hello. Good morning for everyone. I hope you can see my screen. Okay, so yeah, I'm Chau here from Singapore University of Technology and Design, Engineering Product Development Pillars. And today I'm going to share with you our research work in this area on the reconfigurable intelligent surfaces for wireless network powered by the AI technology. Okay, let's start. Okay, so this is a typical wireless communication system, a simplified diagram. Over here, you can see in the traditional system with a transmitter go through the wireless channel, and here is the receivers. So in the traditional wireless communication problems, what we try to do is that we try to optimize or design this transmitter and receiver such that we can achieve a reliable wireless communications. And we all know that wireless channel is challenging. So that's why we have to come up with various transmitter and receiver techniques like OFDM, MIMO, these kind of techniques to help us to improve the system throughput. Going forward, what we foresee is due to the advancements in the material and technology, on top of just optimizing the transmitter and receiver, there is also a possibility that we can also make some changes to the wireless channel. So we call this a smart radio environment in the sense that it's not just designing the transmitter and receiver, but at the same time, we can jointly optimize this channel. We can manipulate this channel and change this channel to make it more suitable for the wireless communications. And how we can change this channel. And one of the recent technology is what we call the reconfigurable intelligent surfaces. This is empowered by a new kind of metamaterials. So if you're looking at the 4 small diagram at the bottom, you just imagine that this is a surface of antennas, okay, made out of new metamaterials. And this surface, you just think about it's a surface of antenna. It can perform multiple functions. For example, it can change the polarization of the radio wave. So when the RF radio wave comes in, it can change the polarization, or it can do the scattering, or it can do the focusing, which means that focus the energy of the radio wave in certain direction, or it can also just absorb the signals. Okay, it can do all kind of manipulation to the radio wave. Such design can be either like the discrete or continuous. Okay, like the diagram at the top left, this is an example of continuous surface, and the other hand, on the right hand side is a discrete surface, which means that on this surface there are multiple elements, and each of these elements we can controlling the on-off or maybe change the phase of the radio wave. Then together this surface will perform some functions. Let's show you some examples that will help you to understand. This is a very initial prototype built by MIT. So over here you can see this green wall. You just imagine that this green PCB wall is the surface that we mentioned earlier on. And based on the paper, this is a 3,200 antennas system, okay? And at that time, it was one of the largest antennas they ever used. So what are this surface looks like? You can see on this surface, basically 3,200 of antennas, each of them is one dot that you can see here, either red or blue. Red means that this antenna is turned on. Turn on means that it's reflective. So whatever wave come in, they will reflect back. The other one, blue, it means that it's turned off, which means that this antenna becomes transparent and the wave can pass through. So just imagine that this is a big surface and every element you can control them by the turning on or turning off. More importantly, this surface is passive, which means that it does not transmit any power. What you do is you just control each element to be on and off, like an RFID tag. So we show you an animation to see how it works. Over here, you can see this dot here on the left, this is the transmitter. And these dotted lines, green dotted lines, you assume this is the green surface. Okay. And of course, this is a 2D view. And then the target is around this direction at the lower left-hand corner. Let me play again. Okay, so what you can see, when this transmitter emit a wave, because of the green surface is on and off, based on some calculations, and what you can see is this, the energy moves towards this direction. Do you see that? Okay, which means that by controlling the elements, each of them by on and off, you can change the direction of the wave. You can reflect some of the energy back, or you can change direction, focusing on certain direction, such that most of the energy your target move towards this target direction. Okay, this is one initial idea of prototype. And later on, this group of researchers from Southeast University in China, they also come up with a prototype as shown here. You can see these two yellow-green surface, yellow gold color surface. These are two antenna surface, okay? And these two, the antennas is the so-called the RS surface. You are acting like a two transmit antennas. Okay, so over here you can see they use this prototype to sending two stream of data to this receiver on the right. And what you can see here is the constellation at the receiving ends. So they are sending two streams of 16 QAM. And you can see the QAM are quite nicely, they know that you're being received. And of course, this one earlier prototype, how we can use this RS surface as a transmit antennas. And this technology also getting attention from the industry. For example, this greener wave from Europe, they've come out with this meta surface antenna as well. Okay, let's look at what they promise. Over here, you can see this, they are set up. So this is the rooms. You can see the figures on the left. This is a room without RIS. So the transmitter is inside these living rooms and receivers is along this corridor. Whereas the other scenarios is the same room layout, but then there is this IS surface at the wall, outside the reading room, okay? Over here, what you can see is the receiving end, okay, the figures on the right. Without the IS, what you can see is this. This is the constellation that you receive, and you can see they disperse all over the space. Whereas with the IS, you can see a very clear 4 constellation, which is the QPSK signals. And this demonstrates that this IS can help you to focus the energy from the transmitter and pass the signal towards the receivers. Okay, so this is one prototype built by the industry. Next, in Japan, an entity Docomo has also started a trial of such metamaterial surfaces quite earlier, and this is shown in 2018. So they have this big surface and they fit on a van, and they move along the van and they measuring, what is the speed of communication they can achieve. More interestingly is the test on 2020. They managed to have these surfaces which is transparent, and you can see, unlike the prototype that you see earlier on, green patch or gold color types of surfaces, this meta surface is transparent in the sense that you can use it as a windows, so the signals passing through, and at the same time you can do some manipulation. For example, focusing the signals to the end users. And again, this is one example to show how promising is this technology. In fact, this technology has been listed by this white paper by Samsung as one of the key technology that could, support or facilitate the 6G communications. And again, this paper also won the IWFC Marconi Paper Award in 2021. Okay, so I hope I give you some motivation examples, how these surfaces can be useful, or it's a promising technology. Next, we are going to introduce you 3 our recent works on how we can make use of these RS communications, RS in the wireless communications. And we show in 3 different scenarios. One is the physical layers, is for the terahertz multi-hop communications. After that, we work on the MAC layers, multiple access, which is the layer 2, when you have multiple pairs of users try to access the channel through this RS, how we can deal with it. And then the third part, we are talking about the sensing capability of RS. If this RS surface is not just for communications, but it also has some extra capability like sensing, that can sense the channel, what we can do, use it. And in all 3 cases, we adopt the AI solution. Later you can see, mainly because the problems can be quite complicated, and we show you how the AI can help us find a feasible solution. Okay, like you heard in the first presentation, moving forward, right, for example, from 4G to 5G and 6G, there's one aspect is to have a higher transmission the data rate. People expecting you are streaming the AR, VR, you are experiencing a higher data rate. And one way to achieve that is that we are moving from the radio wave, which is what in the current 3G or 4G system, move towards the millimeter wave. Because the higher frequency, the higher bandwidth, which means that you can send more information. And finally, moving forward to 6G, we may move towards the terahertz bands. But of course, moving to higher frequency band, there are challenges. One of the main challenges is the high propagation loss. Mainly because this wave, these signals can be easily get absorbed by the water vapor is in the atmosphere. So this making the terahertz communications extremely short range. Okay, the range of communication will be very short. And for us to achieve a feasible communications, we have to find ways to extend this communication range. So that's why over here, what we propose is a hybrid beamforming architecture. So through multi-hop. What you see on the left, this is the transmitter, okay? And then for us to reach the end users, of course, if the user is near, we can through the direct path. But if the user is far away, we'll need to go through the multi-hop. So over here, we assume there are multiple, this so-called RS surface. Okay, so imagine that you have one surface here, one surface here. So the signals can bounce through the first surface and then bounce through the second before you reach the end users. And what we propose is also to reduce the complexity such that we keep only the digital beamforming in the transmitter. And all the surfaces only the analog beamforming. Okay, so what we need to do is to design these two the beamformers such that we can achieve a good signals at the receiving end. Okay, so the problem looks like this. We over here you can see we can write down the received signal to noise ratio at each users. Okay, so each users you get your received signals, and also you may hear some interference. This interference due to the signals to the other the users, and then plus the noise. And our objective is to maximize the sum rate. So typically it's the log 2 1 plus SINR. So we try to maximize this term here, which is the capacity based on the SINR. And for us to maximize this term, the parameters are this F and phi. And F is the digital beamforming, and this phi is the analog beamforming. And we try to design this tool such that this term here is maximized, of course, subject to some constraint like the power constraint, etc. To solve this problem is not an easy task. Of course, when the network is small, like one hop, we can use traditional existing optimization techniques to help us to solve it. But when the network is large, like you have two hops or more, finding a solution using existing optimization techniques will be challenging and quite complicated. So that's why we rely on the recent advancement in the AI, especially in this case, is the deep reinforcement learning to help us find a solution. In this deep reinforcement learning, there are two networks, okay? One is the actor network. This actor networks will be the network that proposing some strategy. They will design the beamformers, assign the power to find what is the best way to do the transmission. And then with this strategy, we do some evaluation. These critic networks, right? Well, based on what you receive, then they will assign some rewards. Okay. So for example, if this strategy is a good one, it will give a higher reward. If this strategy is bad, then it will assign a lower the reward. And through multiple rounds of iterations, then these two networks they converge such that we will get the optimal networks that can propose the best strategy for the wireless transmission. Okay, we skip the details. We'll just show you the results. Okay, so this is the results. In this case, right, you can see the x-axis is the distance, the distance from the transmitter to the receivers. The y-axis is the throughput. Okay, the benchmark is the red colors, which is this one, is the zero forcing beamforming without the RS, which means that if we don't use the RS, just the transmitter do the zero forcing beamforming to the end users, how it looks like. And what you can see here, this is the performance. Okay, so what you can see is this. This benchmark has the poorest performance because for the same distance, it has the lowest throughput for all the schemes. Okay, so this just used as a benchmark. And then next, if you look in the blue and green, this is the case that we use one RS, which is the single hop. Okay, which means that if you put in one RS, the surface, so that the signals can jump over for one hop. And what's the difference between green and blue? For the blue one is the one we use the traditional optimization techniques like the alternating beam, the beamforming. And then the green one is the solution that we're using the deep reinforcement learning. Over here, you can see these two schemes, they perform quite close to one another. And in fact, the deep reinforcement learning can perform slightly better. Okay. And then next, we look at the other case is the purple one. The purple one is the case with two hops, which means that the signals can jump through two RS surface before it reach the end users. For this case, right, you can see we achieve the best performance, the highest throughput for the same amount of distance. And for this case, right, the purple line is based on the deep reinforcement solution because the problem is so difficult that we cannot use traditional methods to solve it. The complexity is very high. Okay, so we can only rely on the AI techniques to help us get a solution. If you're looking at the figure on the right, this is the training the process. Okay, the y-axis is the reward functions, and the x-axis is the steps. The apples that we do the trainings. So 1,000 for 2,000, so on and so forth. This training process is trained over offline. Okay, so before you run the network, you can train this network offline. And what you can see here is these rewards get higher and higher across time and slowly will converge, which means that the network is being trained, and you go further training, you don't get a higher the reward. And of course, throughout the training, you can see the rewards get fluctuation. Okay, because this is the typical AI the behaviors. So it takes some time. The fluctuation is normal. You can see the blue cases, the fluctuation can get low, but slowly will comes out. And for the blue, purple, and green, they're corresponding to different transmit power. So the blue case is the case with higher transmit power, and the green is the one with lower transmit power. So because for the higher transmit power, the solution space is larger, so that's why we expect a higher fluctuations throughout the trainings. Okay, so for this part, right, what we have shown here is this. Moving forward to the higher bandwidth, like the wireless, the terahertz communications, because of the short range of communications, we propose to use this multi-hop IS to help us to extend the communication range. And we show that by using the multi-hops, we can extend the coverage by maybe 50% of coverage. And what we propose is also a hybrid beamforming solution where, with analog and digital beamforming, the digital is only performed at the transmitter and analog at the receiving end. And finally, we also propose a solution based on the deep reinforcement learning techniques to help us find a solution for this problem. Okay, so then we move on to the next topic is in the MAC layer. Okay, just now it's in the physical layers like the beamforming, and it's the downlink, which means that the transmitter sent to the end users. However, in the real world, it's not just downlink, there are also the uplink, okay, which means that uplink means that the mobile, like your mobile phone, you try to send information to the base station. And because you are not alone in this network, so everyone, they want to send information to the base station. So that's why we have to deal with this so-called multiple access. Okay. So yeah, this is the motivation. And what is the new challenge that RS bring into this multiple access is that, in the wireless network, you are not alone. Okay. You are not the only one that want to access this channel. There are people around you, they also want to send information at the same time. Okay, so traditionally we try to, in the multiple access, right, we try to allocate the frequency and time resources such that all users, they do not interfere to one another, and each users, you get your own share of resources to help you to do the transmission. But with the introduction of the RIS, right, this RIS, the surface, they bring in additional challenges. So what are the challenges? One is that this RIS is also considered as a type of resources, just like the time and frequency. This RIS is a resource because it can help you to optimize your channel. So how we allocate this RIS to the end users? Who can access to this RIS? So this RIS is a resource for us to allocate. After we allocate, right, we also need to optimize this RS phase, because this RS, remember, there are many elements. So which elements to be turned on and off, or what is the phase of each element? This is also a problems that we need to optimize. So this bringing extra challenge to the MAC protocol. We'll show you 4 different scenarios, okay, in the uplink scenarios. The first scenarios, right, is just one RS, no single RS, just one surface. But there are multiple transmitter and one receiver. Just like imagine that all the mobile phones try to access the base station through this single RS. Another scenarios is that with also still single RS, but with multiple transmitter and multiple receivers through this single RS. These scenarios you can imagine is like the drone, UAV communications, so that user 1 controlling the drone 1, user 2, they control the drone 2. Okay, in this scenario is what we have the multiple transmitter and multiple the receivers. Then scenarios 3 and 4 are similar to the first two scenarios, just that instead of one RS with multiple RS. So these are complicated problems. And how the MAC protocol design looks like, typically we can divide them into 3 scenarios. One is the centralized approach, which means that someone centrally, you optimize the resources. Okay, you can say that a time slot 1 for user 1, time slot 2 for user 2. Of course, we can also have the distributed MAC in the sense that this is not a centralized solution. So every end users, you make your own decision when you want to do the transmission. And of course, we can have a hybrid scheme in the sense that we combine the centralized and distributed. So the challenges for the MAC is like what I mentioned earlier on, is this: how we allocate this IS the resources and how we optimize the IS parameters. So over here, we consider scenarios, which is the multi-pairs communication. So there are multiple the users, they try to controlling their own drones. So user 1 control their first drone, user 2 control the second drone, so on and so forth. And what we consider here is you can see this portion is we make some assumptions. Okay, first of all, we consider a centralized solution because it's much easier as a starting phase. Then it's a schedule based, which means that someone in the central will do the scheduling. They will assign who will do the transmission based on time. But then what we do is that we dynamically assign this IS. Okay, dynamically we allocate this IS the resources to user 1, to user 2, so on and so forth. And it's for multi-pairs communication. And what we try to achieve, right, is to allocate this IS and the IS parameters without the power control. Let's show you an example. Okay, so this is the protocol that we're going to design. Over here, you can see the x-axis. The x-axis is the time axis. So you can see this is a frame 1. The first time frame, how its transition looks like. Then this is a frame 2, so on and so forth. And the y-axis is the frequency the domain. So over here, we pre-allocate, the first pair, user 1 and UAV 1 is using this frequency band. User 2 and UAV 2 is using the frequency band. So every the users, they are operating at different frequencies such that there's no interference. And what we try to do is this: how we going to allocate these IS resources to different pairs? How many pairs should we use? And how many pairs should we allocate the IS? And then what are the parameters? Okay, this is what we try to optimize. And then in this protocol, right, the first part is the negotiation phase, which I'll show you in more details. Then the second phase is where we do the transmission. So what you can see in this example is this: in the first frame, the second pair, third pair, and fourth pair, they are assigned for this IS. I divide this IS into 3 different groups, and they are assigned to these three pairs. Then in the second frame, I decided, the best scenario is that I decide this IS to 4 different groups. Okay, so these 4 groups, these 4 pairs can enjoy the benefit of IS, so on and so forth. Okay, the negotiation phase, again, you can further divide into 3 different steps. Okay, so over here you can see there are 3 elements: UAV and the end users. They try to communicate, and then there's this IS, the controller. So in the step 1, right, is the synchronization, where the IS, this is a centralized solution. So this IS controller will broadcast some signals that consist of the pilot for these two users to do the channel estimation. Then the UAV can pass this channel to the end users so that these users can take this chance to estimate what is the channel between the direct path. And then they will send this information to the IS, the controller. IS controller will do the optimization to decide, how many groups should I divide, and then assign to which pair. Okay, this is done in the negotiation phase in these 3 steps. And this is how the optimization is being done. Okay, so of course there are power constraint, the IS constraint, how we optimize the IS phase, etc. So of course these problems you can solve using some alternating iterative traditional optimization the solution. But let's say you want to, in real time, the real time, there are many drones and users, they try to communicate. So how we can find a real-time solution in a low complexity is one challenge. And that's why we propose this AI-based solution. In the sense that we call this a multitask learning, okay? In the offline, right, we can generate many type of data through simulation, okay? We can run the search solutions to find what is the best solution, because in offline training, we don't really care so much about the complexity. And then we'll train out this learning, multitask learning, the modules. So once this module is being trained, right, in real time, based on the scenarios, how many pairs of users, what is the channel to condition, straight away we can come up with the solution. How many pairs we should allocate, and which pair they will get optimized the RS. And then this will reduce the runtime the complexity to linear. Okay, we'll show you the results. Okay, so over here, what you can see is this in these figures, right? The x-axis is the number of UAV to user pairs. Let's say 1 pair, 2 pair, 3 pairs, so on and so forth, to 8 pairs. And this is the throughput. Okay. So different lines corresponding to different RS groups. So for the L equal to 1, which means that we allow just one group. Okay. The red one is for 2 groups, which means that I can cut my RS into 2 groups to support 2 different pairs. And then this one for 4 and 8. And the red one is the benchmark without the RS. Okay. So we can see using the RS definitely will helps, because it helps to improve the channel. Okay. So that the users can get a higher the throughput. And then over here you can see a drop over the time. The drop is mainly because when we try to allocate the IS to more groups, right, we improve the fairness, okay, which means that more pairs can enjoy the benefit of IS. But because of this fairness, the total throughput of the network will drop, which means that someone that will enjoy, they get higher the throughput, but overall the whole network, the throughput will drop. Okay. And then if we compare this AI-based solution compared to the traditional scheme, we achieve a slightly better the performance, mainly because when we do a training, we're using the associative search. But of course, if you're comparing the complexity in real time, the AI solution will be lower than we do the optimization in real time. Okay. So as conclusion, right, we looking at how we can use this RIS to assist for multi-pairs communications. We design and propose the transmission strategy. We design the MAC protocol to facilitate this transmission. We real time jointly optimize this IS group and also the IS the configuration, such that we can maximize the whole network the throughput. Okay, then in the last part, right, so what we're going to move forward is the spectrum learning. Okay, what is this spectrum the learning? So the whole motivation is this. So right now, what you can see the previous example, the IS is to help us to do the communications, okay, to help us to send the information, so on and so forth. However, we are moving forward that, if this metas the surface, this IS the surface, it is not just use it for the communications, but how about it has some kind of smart learning, such the sensing capability. It can perform some sensing, okay, and then how we can use such features. Okay, so over here we consider a spectrum sensing scenario. Why we need this spectrum the sensing? We know that IS can achieve some performance, so on and so forth, but this may not be always the case. So for example, if one user they try to send the information, let's look at the next slide. Okay, it's easier. Okay, so let's say for this scenario, okay, these users try to send the information to the base station. Okay, you can see it may send assist by this IS and also assist by the IS at the top. Okay. But because you are not alone in this network, there can be someone else nearby. And let's say this user, okay, these users, sending some information as well. And if this user and the intended the user, they are close to one another, so the signals from these users may also be reflected by the RS to the base station. And such reflection, right, because it's interfering, is interference, we show that later on this may do some harm to the overall performance, because this RS will also help to to forward this interference. Hence, if this RS, right, has some sensing capability, it can sense that, hey, right now it's not just the useful signals, but there are some interference as well. Then we later on will show to you that maybe it's good we can just turn off this RS. Okay, so if this RS can dynamically turn on and off based on the actual scenarios, whether they are interference or not, it will benefit the overall network performance. So we try to introduce some kind of sensing capability to this RS. Over here, what you can see is this. With the offline training phase, so this offline training, basically we just train this RS to differentiate the signals. If these signals consist of just useful signals or they consist of interference. Okay, then once this network is being trained, right, later on when in operation, this RS can do the sensing, and based on the results, it may decide they want to turn on or off. We consider a very simple scenarios. Okay, in these scenarios, we consider just four classes. So it's a classification the problem. In the class 1, in the sense that just purely noise. Okay, no one is doing the transmission. In the class 2 means that only one user do the transmission, the user 1. The class 3 is the user 2. The user 2 do the transmission. And then the class 4 is the case that both users, they are doing the transmission. Okay, so we train this neural network to classify the scenario into 4 different classes. Based on the classes, right, if there are some interference, 2 users are do the transmission, then we do a simple on-off the control, so that we just compute and estimate the SNR. If I turn on this SNR, turn on this RS, and if turn on this RS and the interference they reduce the SNR, then I will turn this RS off. Okay, so it's a very simple strategy. And let's show you the results. This is a four class classifier, and we're collecting some RI and Q, the RF signals, and then we use it to do the training. Over here, what you can see is this. For this case, we can achieve like 95% of accuracy, which means that 95% of the time we can correctly classify the channel. We can know is single user or 2 users they do the transmission, or just purely noise. Then with this sensing capability, right, we run some simulation, like how if we can dynamically turn on and off the RS, how it can be useful. So this is the scenario set up. So you can imagine that there's this building here, there are multiple RS, and there are two users here. This user at the bottom is the desired the users. So these users will send a signal to the base station. And then there's the other one user here is the interfering the user. This user will create the interference to the signals. Okay. And this angle here, the delta, is the angle between these two users. So we can see from this figure that if this delta is very small, which means that these 2 users coming from the same direction. So high chance that these users will create the interference, because the eyes cannot differentiate the users is coming from this UD or the interference signals. So they will forward all the signals to the base station. Okay, so the base station will receive the interference. But if this angle is large, right, then RS can be turned on, because RS can differentiate these 2 signals. They can just forward the signal from UD, and then they will reject the UI signals. Okay, we'll show you the results. If you look at the figures at the top right, this is the parameters of delta, the angle just now. This is the achievable SNR. Okay. Okay, so if you look at the blue line is the case that RS always on. Okay, if I always turn on the RS, so what you can see, if this angle is small, when 2 users coming from the same direction, so you can see this SNR is very low, because the IS also forward the interfering signals. They can't differentiate the two signals. It will forward the interfering signals. And then as this angle get higher and higher, right? Okay, like 90 degree or even up to 150 the degree, then these two users are separated. Then in this case, when I turn on the IS, it will be helpful because IS can differentiate these two signals. They reject the interfering signal, just forward the signal from UD to the base station. So the SNR get increased. Whereas for the case of the IS always off, right, which is the green line, okay? Because of the IS always off, so you can see the SNR does not change much. Of course, the two users, because based on the distance, they may impact the SNR a little bit, but because it's always off, so they don't really change much. Next, we see the red one. The red one is this, the U-shaped curve. So we can see by dynamically, based on the sensing capability, I can sense, I know there's interfering or not. I can dynamically on and off the IS. So we can see I enjoy the best of both worlds. When this delta is small, I know that there's interfering, then I can turn off the IS. But then when these users are moved far away, the angle is wide apart, I can sense that, even though there are interference, but the SNR is high, so I can turn on the IS. So this sensing capability will help me to decide, when I should turn on and off the IS. Then I can achieve the best performance. Okay, next we show you the case when we have multiple IS, okay, in the figure at the bottom. This is a case of one IS. The first three bars are the one IS, 2, 3, and 4 IS. The white color bar is the case that IS always on. Okay, so you can see this is the throughput, the SNR when one IS always on, this 2 IS always on, 3, 4, and 5. So you can see when I have more and more IS always on, it will help, okay, as the IS get increased. The reason is that I have the diversity, okay, because all the 5 IS in different direction. So definitely some of the IS will help the transmission. So by increasing the IS, it will help, okay. For the case of IS always off is the gray color one in the middle. So you can see no matter, because they are always off, so no matter how many IS, it doesn't matter. The throughput is always the same. The SNR always the same. The last case is the black solid bar. This is the case that if my IS is the spectrum learning. So you can see for this case, as the IS get increased, I get higher and higher SNR. I get the same trend as IS always on. And also for all the cases, right, with the spectrum learning, I always better than the other the two schemes, always on and always off. Because I can learn it, I can do the real-time the sensing. I can dynamically turn on and off. So I always achieve better than the other the two schemes. So for this part, with this conclusion in the sense that, we're looking at, this IS, if I have the smart capability doing the sensing, so how I can deal with it. And we show that, by doing the sensing, I can turn this IS on and off. And it will helps me to achieve a better overall system performance. Okay, I think that's all for my presentation. So these are the 3 areas that I show, how the IS can help in the future communications, and how the AI can help us to provide a solution to optimize this IS network. Thank you.
Thank you so much, Professor Yuen Chau, for your illuminating talk on AI-assisted RIS wireless networks. We'll now move on to our question and answer segment. And I believe we have a question already from our audience. And it says here, the range extension by RIS depended on the loss of RIS. What is typical loss? Professor, your thoughts?
Okay, so I think you're talking about the first topic that, if I mount multiple hops, how does it help? So, and of course, you're asking about, what happens if when I do the hopping, the signals get weakened. So, okay, so there are this this problem, there are multiple aspects. So first one is this. Typically, the IS that we consider now is a passive device, which means that this IS, when we do the reflection, like focusing, etc., we are not pumping additional signals. Okay, so it's a pure passive the device. Okay, so if this is the case, right, you are right that these signals will get weaker and weaker. But because of this eyes can help you focusing the signals, so then it depends on how many hops and how well you can do the beamforming. So if you can focus in the signals, what you focus is higher than the loss, then by adding additional hops, it will help. Okay. Then of course we have another scenario in the sense that if this IS is not passive, if you can make it be active, it can amplify the signals, then of course it will definitely helps a lot. Okay, so I hope I answer your question.
Thank you so much. And of course, that was a very insightful answer, Professor. Now we have another question coming up, and this says, for RIS, we would need to know where is the TX and RX. Does it mean that it needs to intelligently compute and track both and direct the beam? Professor, what do you think?
Okay, so you are right that okay, for this IS, like we shown here, for us to do the beamforming, to focusing the energies, I do need to know the channel. Okay, I need to know what is this channel from the transmitter to the IS and the IS to the N for end users. So I need to know for all this channel. Okay, so I do need to do the channel estimation. And for the channel estimation, there are different scenarios. Some people, they assume that I know every hops, every individual channel. There are some people, they do the beamforming based on the composites channel, which means that I don't need to know the individual hop, but I need to know the overall for the channel. So these are the most recent works that people, how they work on the channel estimation. I'm not very sure is there any blind scheme, which means that the IS use without knowing the channel. I'm not very sure someone has been working on that, and then how we can find a solution. This part I'm not sure. But right now, most the literature that I have seen, we assuming that we know the channel and we need to do the channel estimation.
Thank you so much, Professor, for helping to answer that question from our audience. We have another question here, and it says, how is the channel estimated in DRL-based multi-hop RIS optimization?
Okay, so if you're talking about this work, right? For this work, we not focusing on the channel estimation. So we assume that all these channels are perfectly known, is given to us based on the given channel, how I design the beamforming. Okay, so in this work, we didn't do the channel estimation. And you can refer to some others work, that we work on the channel estimation. So in this case, we didn't solve for the channel estimation the problem. We assume it's perfectly known.
Thank you so much. We've got a couple more questions for you, Prof. This next question is, in page 38, what will happen when the desired user becomes an interfering user and the interfering user becomes a desired user?
Okay.
Yeah,
so
that's the question.
I think what. Okay. So I rephrase the question based on what I understand. You are meaning that if these two users, they are both desired and they are both interfering to one another. I guess this is what you are saying. Okay, so that is not the scenario that we consider, because for the cases that you mentioned, right, both are the desired the users. By right, the map protocol should assign the resources, like different frequency or different time resources, so that the map protocol will handle that already. So the scenarios that we consider here is like this. For example, at the cell edge, this user is served by this base station, and then the other the users here is served by another the base station. So because we use the frequency, then they create the interference. So this is the scenarios that we consider. Because this one by right for the case that you mentioned, right, by right the MAC protocol should handle that if both are desired the users.
Thank you so much, Professor, for just diving into that question for us. We have another question over here, and it says, where is the best spot for this RIS to be placed in an urban area? What do you think?
Okay. So I think is what you so this is a hard question. In fact, there are people who has done research, on the placement of RIS. Okay, so typical, the typical answer is we typically would like to, when you have multiple RIS, of course we would like to as diverse as possible, as you distributed them. But then for the case of single RIS, if you have a pairs, where you're going to place this RIS is important as well. And if you look at, in recently we published one of the paper. In that paper, we assume that if this RIS we hanging is in the sky, for example, carried by the hot balloon or the UAV, just an assumption. So between the transmitter and receiver, where I should place this RIS? We recently published a paper is on this topic, and it's not. And actually, the conclusion is not just the placement. It's not just the SYZ, the position, but also the angle. Because this RIS, you have the angle, how you going to face which direction. So it's a 6 dimension, the optimization, the problem. So you may refer to that paper to get the answer for your question. So it's a long research, the topic.
Thank you so much for addressing that, Prof. We have another question just coming up into our questions, and this is, which software is used for RIS assisted wireless?
Okay, when we run simulation, typically we use the MATLAB to run the simulation. And when you ask about the software, so usually we write our own simulation to in MATLAB or Python to run the simulation. Then of course for the case of spectrum for learning, right? This one we use the USRP. It's a software defined radio to help us collecting this RF trace. It's a NI based solution, National Instrument.
Okay, wonderful. And I've got to thank the audience for just continuing to send in questions. We've got one more over here, Prof. And this one is, frequency at 100 gigahertz and above will incur huge propagation loss. Signal is not regenerated with RIS. What is the max hops supported?
Okay, so this one we don't have solution. So if you're looking at the first part, right, the solution that we show you the results is for two hops. In fact, we don't even have the solution for three hops and further. The main reason is that even just to compute the solution is too complicated. Even for example, in this case, we want to use the eye to do the training. It's too complicated for us to find a solution for more than two hops. So yeah, so I don't have the answer for you, like how many hops is the maximum, etc. Unfortunately, now it's beyond the complexity that we can solve the problem.
Thank you so much, Prof, for that answer. We have another question over here, and this one is wanting to know, our audience wants to know, is the concept of RIS viable commercially? What do you know about this, Prof?
Okay, so that's why in the first part I getting show you some examples. So we believe that this RIS is promising. So you can see that there are already real prototype that people has been doing the testing. Like Docomo, you can see there are also this surface is transparent. And this group of Greener Wave from Europe, they also have a working prototype as well. But of course, we we do not know. Okay, so at least right now, what we can see is this is a promising solution that we already see a working prototype, and people has shown that this surface, this IS can bring benefit. Okay, but eventually whether it will become a truly successful or not, I think only time will tell us.
Great. One more question over here, Prof. And this one says, what size of RIS is assumed in this simulation in page 18? The performance may be dependent on the size. What do you think the answer could be to this one?
Yeah, okay. I forget what is the size that we use in the simulation, but you are right that the performance based on the size. Okay, whether you have a small surface or a large surface. But of course, when you have a large surface, more elements, there are more parameters for us to optimize. Okay, so there's always a trade-off, because when you have more parameters for you to do the training estimation, for you to optimize, can you get a good solution or not is a trade-off. So I forget the size. You can check the paper, but you are right that the performance is based on the size of the surface.
Thank you so much, Professor Yuen Chau, for helping to answer all those questions from our very participative audience. I think we had almost 10 questions over there. Thank you so much for that, and of course for your illuminating presentation on AI-assisted RIS wireless networks. Thank you so much, Professor. And I feel so excited about the future right now, with this morning's talks giving us an idea on the roadmap towards 6G and promising results on RIS wireless network empowered by AI. Well, it's time for us to have lunch right now, with plenty of food for thought from the morning sessions as well. And we'll start the afternoon sessions with discussions on the validity of Shannon's capacity for 6G and beyond, multi-mode MIMO communications beyond beamforming, localization of things in beyond 5G ecosystems, and deep reinforcement learning for control of large-scale communication infrastructures. We'll see you back here in about an hour at 12:45 p.m. Singapore time. See you then at 12:45. Now, in this session, we will discuss on the suitability of Shannon's capacity for 6G and beyond, and the proposal of modified Shannon's capacity, which shows that higher modulations will result in lower channel capacities. Now, our next speaker is an IEEE Fellow and Vice Dean of the School of Micro Nano Electronics, Zhejiang University. He was the member for IEEE University Program Ad Hoc Committee from 2011 to 2013, and also a member of the editorial board for proceedings of IEEE in 2013 to 2018. Now, he's also the editor-in-chief of IEEE Transactions on Microwave Theory and Techniques. Ladies and gentlemen, let's welcome Professor Ma Jianguo.
Thanks, Yuen, for the introductions, and good afternoon, everyone. Today, I will discuss about the Shannon's formula for future applications. Okay, it is well known in 1948, Shannon published his classical papers entitled A Mathematical Theory of Communications. In this paper, he defined the channel capacity at the right upper corners. And in the paper, he described the general communication system in the figure 1, that is direct copy from his paper. Here, he described that the noise sources separate from transmitters and receivers. And also, he defined the channel is a normal medium for transmitter to receiver, and could be a wire or coaxial cables, a band of radio frequencies, a beam of light, etc. in the paper. And next year, he published another classical papers entitled Communication in the Presence of the Noise. In this paper, he proposed the famous Shannon's theorem. And in this theorem, he propose the mathematical expression for the maximum available channel capacity C in the equation number 19 at here, also direct copy from his papers. And here he described the power P as the average transmitter power in the equation for defining the channel capacity. Then he didn't mention for any other part of the general system in figure 1. And for example, for communication, we have the sender and we have the receiver also. What is the power received by the receiver side? In this theorem and in his paper, he didn't mention for that. And also we use this power P to describe the maximum available channel capacity. And that equivalently might be for the broadcasting, because for broadcasting, we care about the power sent by the transmitter, and we don't care about the power level received by receiver. Like right now, I'm talking in my office, no matter how I would be so loudly, anyway, I have the maximum power levels. However, if there is no such wireless communication system and the audience cannot hear my voice, that means for the receiver side, that receives nothing. Therefore, for meaningful communication, we have to define the power levels in the receiver side, then to determine what will be the maximum capacity can be received rather than be transmitted. That is the main point for my talk. And also in his classical paper in the theorem 2, he defined the noise. He supposed that the noise is wide thermal noise of power N. Okay, then in his figure 1, this noise N used in the channel capacity equation might be from noise sources. However, we know any hardware system that will contribute additional noise due to the devices being used. For example, even in old days, there's the communication system worked out by the vacuum devices, because at that time, the transistor haven't been used yet. However, for those vacuum devices that have noise, not only for the white thermal noise, there are also other noise like the frequency very high or the flicker noise in the relative lower frequencies. Therefore, from this theorem, it didn't mention other noises just for the white thermal noise. And for this channel capacity expression, there are another form that is in the P plus N over N can be rewritten as 1 plus P over N, or signal to noise ratio. Now, for this signal to noise ratio, we have to identify where this reference plane it is. If we talk about this the input reference plane for the receiver that has its signal to noise ratio. However, if we are talking about there is a signal to the destination of digital baseband, then for any digital baseband, it requires minimum signal to noise ratio to guarantee the digital baseband can work out the necessary useful message. Therefore, there is a different place to have the different signal to noise ratio requirement. Also, for wireless communication up now, we all assume there are two assumptions. Number one, antennas, no matter for transmitters and also receivers, then the point sources. And the second, the receiver side is located in the far field region compared to the transmitting side. Okay, now we look at this point source. Then for any point source that radiates electromagnetic wave or radio wave uniformly as a spherical waves. If the radius or distance from the point source double, the energy density will be a quarter. That is the basic principle in the free space. Therefore, now for any wireless communication system like here, we have the transmitters with the transmitter antenna gain GT and with the maximum available transmitted power PT. P means transmitter. Then for the receiver side, we have the antenna with the antenna gain is GR. R represent receiver side. Of course, the received power level is PR. For free space that has a so-called path loss, then that path loss can be get in the free space like the L for pi d over lambda bracket square. Okay, for practical application situation due to multi-path reflections, due to the buildings, due to other environment issues, of course, this path loss will be much higher than this L. Now we discuss the so ideal case in the free space. Therefore, according to any kind of the system textbook for the RF, we can get the receiver side, the power level PR equal to PT times the two antennas gain and also times the path loss. Okay, that's the things. Now we come to any general receiving structures. We have the antennas and we have the RF front end with added noise figures. Okay, those noise contributed by the whole front end hardware side. And also for recovering any meaningful message, then we have to have the minimum required signal to noise ratio SNR min for digital baseband. Therefore, from the textbook, we can get the minimum power level can be detected by any wireless receiver. The unit is the milliwatt, and then the KT, K is Boltzmann constant, D that is the temperature of the environment. Here, W is the bandwidth. We use the same, there's a symbol as Shannon used originally, and also NF and the minimum signal to noise ratio requirements. Now, for the transceiver side, then we modify the classical channel capacity equation into following equation here. There's a W, the bandwidth keep the same, also log keep the same. Then instead of using the wide thermal noise N in the original expressions, we use a minimum detectable power level P min for any wireless receiver side, and also for the power received by this receiver to replace the power transmitted averagely by the transmitter in the original Shannon formula. Now we substitute PR in terms of the PD, GT, GR, as above mentioned. We can get this modified Shannon capacity, okay, for the channel. Then the modified Shannon channel capacity here. In this equation, that include the parameters for the front-end hardware system, mainly for the noise edit and minimum signal to noise ratio required by the digital baseband. Okay, that is for this modification. Then in following part, I will use this equation to discuss this possible maximum channel capacity. Now, that is more graphically described. There's noise floor or the white thermal noise and minimum detectable signal level for the receiver. In the upper left corners, that is the general environmental noise, normally called a noise floor. And any hardware receivers, it has additional contributed noise figures. And for the same environment, different implementation, we can have the different NF noise figures. That strongly depends on the technique to design and implement the receiver. Then we have another required minimum signal to noise ratio by the digital baseband. Therefore, here that we have the P minimum. And also for any hardware receiver, then we have to guarantee this received signal and deliver to the baseband. The signal will not be distorted or that is so clean without any interferences. However, due to the nonlinearity for any hardware system in the RF front end, if the signal level for the received exceeds certain limits, then the output signal will not be so pure the received signal only, and also there are other signals. The first one, that is the self-mixing due to the third harmonics. We call the IM3 intermodulation 3 or M3 here. Then if the received signal level here higher than this maximum, this for spirit-free dynamic range, then the received signal delivered to the baseband will not only contain the whatever the sender sends, and also the self-mixing signal there. Particularly if there are multiple channels, for example, simultaneously one channel used for one user and another channel for another user. However, those two signals, they come into the same receivers that will have the cross interception or cross interferences. Okay, therefore, for avoiding such kind of the interferences, as long as we can keep the received signal power less than maximum required signal level for spirit-free dynamic range or SFDR, the output from the front end delivered to the baseband digital one will contain only the useful signal originally sent from the sender. That means no matter how strong or how high power level will be by the transmitter, any practical receiver, it has its own maximum received signal there. That is the PR maximum. And for different implementation of receiving hardware system, that will have different maximum RFE for SFDR. Then from this point of view, we just replace previous slide for the modified the channel capacity, the expression here. We put this maximum the SFDR here. Then that will be practically for any dedicated RF wireless receiver system, that maximum available channel capacity will be like this. As I mentioned before, this spirit-free dynamic range or SFDR strongly depends on how to implement this hardware system. Of course, for different operating bands, frequency band, and different technology to implement the receiver, this SFDR will be different. That means maximum available receiver channel capacity that depends on the hardware. And that also provides us another angle. How could we design or even optimize our wireless communication system according to the given channel capacity requirements and also hardware design parameters? For the original Shannon channel capacity expression, it has nothing to do with the hardware implementations. Okay, for example, if we use the bandwidth at 200 kilohertz, that is for the 2G, the GSM or GSM 800 standard. And we use here at the general normal wireless communication, the RB maximum will be the minus 30 dBm here for the spirit-free dynamic range. And we assume for the different minimum received signal level, then substitute into these equations, we will get different maximum available channel capacity, like these figures in the up right corner. Okay, that gave the minimum required signal to noise ratio for the digital baseband from 6 dB, for example, to 14 dB. And also here, a horizontal axis that represent the noise figures required by the hardware implementations. Then that is available the channel capacities from the 5.3 megabit then to the 4.33, for example, depend on what is the design parameters. For example, if we design our RF front end, this has the maximum noise figure at the 8 dB. Okay, that is quite a stringent requirement already. For most of the practical RF system, it is not so easy to achieve that. Suppose here, then we can look at what is for the baseband requirement. Suppose we need to get the maximum channel capacity for 5 megabit. Then we get this signal to noise ratio that will be a little bit higher than the 7 dB. Here is in the right lower corner. That is the general relationship for the digital baseband, the minimum signal to noise ratio and the bit errors. Therefore, we get that is the 7 bit here for the signal to noise ratio. Then we can find, okay, for this the BPSK or QPSK modulations, then the 7 dBm that contribute roughly that the bit error is in 10 power minus 2 the order. However, if we want to get a more higher modulation, then the bit error rate will getting lower. Okay, then suppose we want to get more high modulation scheme. Now we come to here, the 12 dB for the minimum signal to noise ratio. And now that is the maximum available channel capacity will be only 4.67 megabit. And also we can find what will be the modulation scheme for the bit error ratio. If we require the bit error ratio, for example, that is 10 power minus 4, that now we can have the 16 QAM for this modulation. However, if we use the BPSK and so on, we can get the 10 minus 9, that is the bit errors. Okay, then we can choose other things. For example, if that 8 dB noise figure that is not so easy to be achieved, then we have to reduce the requirement come to the 10 dB for the noise figures. Now for the 10 dB noise figures, if we would like to get the same 5 megabit the data rate, unfortunately, there is a signal to noise ratio data to the baseband will be only 5 dB. And if we want to increase the signal to noise ratio, for example, come to more higher, then unfortunately, the maximum available channel capacity will reduce to like this. Therefore, we can look at here, then back to this signal to noise ratio and the bit error to calculate whatever we can find. Therefore, from this, we can use this graph and equation to design our hardware system to deliver certain channel capacity. Okay, that is the advantage for this modified channel capacity expressions. And that is to illustrate for different this channel bandwidth. Of course, we will have a different channel capacities. However, that is not linearly increased from one to another. And here give for the different bandwidth from 1 megahertz to the 1 gigahertz. Again, we assumed there is a spirit dynamic free the maximum power level for the receiver keep the same -30 dBm. Now, from here, we look at if we increase the bandwidth from 1 megahertz to the 1 gigahertz. However, we keep this hardware system, the noise figure as 8 dB. Now, we can find when we increase this bandwidth, keep the hardware design requirement. Now, we also keep the same requirement for the signal to noise ratio, SNR minimum. For example, here is a 7 dBm. Now, the channel capacity from the 1 megahertz that respect. Thank Yuen again, and sorry about the interconnect connections. It might due to the international connection from mainland China to the overseas. Okay, anyway, now I'm talking about if we use a more higher frequencies and with more wider bandwidth, what will be the channel capacity available for both the two frequency band? And there are two comparisons. The frequency band one, that the millimeter waves, the central frequency around 25.875 megahertz, given by the International Telecommunication Union or ITU, and another that is the first terahertz band for the wireless available assigned by the ITU, the central frequency at 285.5 gigahertz with the bandwidth available 21 gigahertz. Now we substitute those two frequencies and also bandwidth into the channel expressions for my modification expressions. We assume everything will be the same for the operating environments, the noise figures contributed by the receivers, and also distance between the transmitter and the receiver, only to change the frequency and the bandwidth. We expect that the channel capacity for the higher frequency will be higher. However, based on this modified channel capacity formula, those two comparisons now shows that the lower frequency band actually provide more higher channel capacity available theoretically. Okay, that is different from the previous in the literature. Of course, the precondition, please remember, precondition is the same distance, the same hardware, noise figures, everything the same, except for the operating frequency and the bandwidth. Okay. Now, From that modified equation, we can know if we increase this transmitting power level, of course, we could increase the channel capacity, and that is their ceilings. We cannot increase unlimited for the transmitting power level. And also we have the transmitting and receiving antenna gain G and GR. From this equation, we can understand when we keep the transmitter power level PD and we increase the gains for the transmitting antenna and the receiver antenna, that the channel capacity will be increased. That means more higher gain for the antenna. Then we change the antenna from omni direction to the directional antenna, or in other words, for directional antenna that will provide us more higher channel capacity like this. Therefore, if we use the antenna elements that is not directional, however, we form the antenna array, then that we can control the beam. Here, there's a beam that is fully directional. However, when we use this, that in the data beam direction, that will have the higher density of the power level. But in other part of the space, there are no such radiated powers from transmitter. That means if we use the directional antenna array, the spatial coverage will be changed. Of course, we hope also we can have the high gain that the direct antenna, or there's a spatial coverage. Then we can use the MIMO system, so-called the beam steering. That is the fully directional and also spatial coverages. Like here, there is the cartoon showed. Then that change the directions and we try to cover everywhere. But another problem, that cost is the operating, that is the time sharing. That means we cannot cover the every place with the same time. We have to scan there's a space to in order to get high capacity. That means that is not averagely, or we define only for the peak capacities for only one possible direction at one given time slot. If we are talking about there is a peak capacity, it's not the capacity constantly, then we now look at this MIMO system, maximum multiple input, multiple output. Suppose we have the multiple transmitters from transmitter 1, transmitter 2 to transmitter M with the same power levels, and for the peak power in the space, that is not, there's each antenna's power level M times, but it's M squared. Why? We have the so-called, there's a Huygens principle, that is like the interference to combine in some place of the space and also cancel each other's. Okay, that is for the light wave. There is a diagram that is well known. Light wave is also one kind of the radio waves, only frequency much higher. Therefore, if we use more antennas to form this MIMO system, then in the space that will have the similar phenomena in principle. That is for the different there's point sources with the different numbers, and that form the different spatial distribution of the energy level. In average, that is average for area, but for the different point particularly, that will be higher density point or the lower density point. Therefore, in the spatial, if we use MIMO system, then those energy distribution in the space will not be so uniform. Then that will the peak and the lower, and with this formula, if we have identical transmitting power with the same power level for each element. Now that the peak power will be much higher than just sum of the individual elements. Okay, then the noise floor for the same environment might be the similar. Therefore, the peak capacity will increase. That didn't discuss by the original channel capacity expressions, and also that is not discussed in the literature for such interference issues. And how could we make use of the original Shannon expression for describe such data peak capacitor instantaneously? Okay. Now, as previously discussed, we increase the GT and the GR in order to get a directional antenna array. However, for most of the practical implementation in the literature, they use the antenna element without the direction and to form the directional antenna array. Why could we use this direct antenna to form the direct antennas array? That will provide us more higher gain for the antenna array. Therefore, in future, or for 6G, for example, with a direct antenna element to form the direct antenna array, that will might be more higher channel capacity available. Then we discuss more another issue. Now, in all the literature, when we discuss the wireless communications, as we said in the previously, the antenna are considered as the point sources, and the receiver antenna is located in the far field region of the transmitting antenna. And we know the basic microwaves guided by the pointing vectors or by the Maxwell equations. The wave impedance generally that is complex. The electromagnetic wave is a vector wave and a complex quantity, and the wave energy also complex. However, for the far field region, we assume or approximately that the wave impedance will be the real and radial wave change from vector and complex wave to the scalar wave, and wave energy will be only real. Now, that for far field region, we have this propagation. However, look at now with practical applications. Suppose we are using Wi-Fi that is so popular now, and we have the pad, the antenna on top. We assume that the point source, according to the basic electromagnetic theorems, if we have the one point source just above this ground, perfect conducting ground, then the electromagnetic waves above the upper half space will be there's a so-called image point source, just opposite as the mirror reflect from our real antenna point source. That the distance will be here. Suppose we have the 1.5 meter to use our laptop, and now that's the distance for the real point source and the immediate point source will be 3 meters, and the general far field condition, that is the distance from the receiver side to the antenna side, is 2 d squared over lambda. Lambda is the operating frequency of our wireless, that is 4.12 meters. That means if we are using our laptop for the wireless and the far field assumptions, we are far field compared to the wireless hot point that 150 meters away. That means if we want to satisfy the far field assumptions, we have to use our mobile devices away from the transmitter 150 meters. I think no one uses that. Like now I'm using wireless connections, then my laptop is so close to the wireless point, only a few meters. That means we are no longer in the far-field regions, and we are just within this mixed energy region. How could we define the Shannon capacity according to the original Shannon expressions? Because that is in log form, and energy power must be the real numbers, and the noise figure that is must be the real number. But now we have the problem because the energy itself, that is not real only. For example, we have these connections, and that is a primary, this inductor and the secondary, and the two coins coupled each other that we learned from the high school already. But that is really another kind of wireless. If we separate the primary and the secondary coin far and far, then in between that wireless channels. In these wireless channels, the impedance will not be so real, the energy also not be the real. And how to describe this field? Then what is the capacity can be defined? That means for existing the 2G, 3G, 4G, and the 5G mobile communication, we assume far-field region, that in this region for the operation. And however, now for more wireless, we are using this, that is for the advanced wireless or 6G beyond. Now, this field no longer the scalar wave, is a vector wave governed by pointing vector. And impedance is so complex, it's not real, and energy described mathematically, that is the complex energy. Okay, then we cannot put the complex the numbers here into the original Shannon's equations. Therefore, we just propose might be for this, we just use the energy, there's a modulus. Then also instead of using the white thermal noise N in the original equations, we just put the P mean here to describe that. Therefore, that is another modifications. There were no mathematic there's a background about that. Okay, only the proposed. Okay, now come to the near to the end of my talk. This picture obtained from the internet that was to show the Tesla's experiment in 1900s, and there is the they do this high voltage bars and to create the AC signals, and from this we can also generally consider that the transmitter and the receiver antenna is also receiver. That is so obviously the energy transmit from these transmitters only partially reach the receiver side. Therefore, the meaningful channel capacity definition should be considered the receiver side rather than for the all the energy transmitted from transmitter side. Then how to describe this channel capacity? That is a core issue for my talk. And also that is now the practical situation for the wireless applications. And for future, we get more high and high data rates, and we will get more closer and closer from the transmitter to the receiver. And what will be the future? We don't know. Then I use the Mr. Shannon's the saying. We know the past, but we cannot control it. We control the future, but we cannot know it. Now we know the classical Shannon capacity expressions. Then we have no control about the past. But now we have our future. We use the 6G, but the environment situation will be different from the pre-assumptions that time Shannon did his expressions. What should we do for the future? That is my main point. Now that is the last slide for my talk. I would like to quote the Yogi saying to end my presentation here. The future and what is yet to be. Okay, that is my talk. Thanks for your attention.
Thank you so much, Professor Ma, for that presentation on Shannon's capacity. And now I believe we have a couple of questions from our audience, starting with this one. And it says, what is the rationale behind using P minimum instead of noise power in the SNR definition?
And, okay, as I just said or explained in my the earlier few slides, for the white noise, thermal noise given in the original Shannon papers, that is not total noise contributed by any receiver hardware. For any receiver hardware, it has not only for the white thermal noise or noise floor, and also it contains the flicker noise, for example, high frequency noise, and so on. And also depends on the hardware implementation, the skill. That means the minimum power level achievable for the receiver side or P minimum. That is the lowest power level any receiver can get. If signal level lower than that one, even higher than the white thermal noise, but this receiver cannot get the signal. That is the definition for the P minimum. That is the reason why I use the P minimum to replace the white thermal noise N. I don't know whether that is clear enough for the questions.
Thank you so much, Prof, for deep diving into that one. And I think we've got time for one more question and maybe a couple more. This next question is, what are your thoughts on quantum limited, I'm not sure how to pronounce this one, is it Holevo or Hovo? It's spelled Holevo, right? So I'm going to assume it's Holevo capacity for post-Shannon communications in 6G. Your thoughts on that?
Oh, sorry again. I
Okay, let me have the
didn't
question
get
again.
that is what is the for the HOT. Maybe it's another kind of noises. Oh, I'm not clear.
Yes, the question is, what are your thoughts on quantum limited, and the word is spelled Holevo. I'm not sure it's pronounced Hovo or Holevo.
Okay.
Holevo capacity
Okay.
for post-Shannon communications in 6G.
Yeah. Okay. That is. I don't know whether I get the point or not. That means for the quantum, the limits. Okay. Then I think that is another issues for the wireless communications in future. If we use the system or the application scenario will reach a quantum limit, then we have to consider the quantum effect. But from my understanding at the moment, the most of the practical wireless system, then from system point of view, we didn't consider the quantum limit yet. However, from original Shannon equation, that I think didn't contain or didn't consider this quantum effect due for that. Of course, that might be related to the hardware implementation. What kind of the physics inside you base on? If we have to rely on the some quantum-based there's a receiver or transmitter, we have to consider that phenomenon or that principle. I don't know whether I got the point. I get the enough message for that.
All right. And of course, thank you so much, Professor Ma, for your presentation on Shannon's capacity and also for answering those questions from our audience. I wish we could chat more, but there's just only so much time that we have. Thank you once again, Professor Ma.
Okay. Thanks. Okay. Thank you, Mike.
Now, we hope you enjoyed that presentation as well as Q&A session. Now, our next presentation will discuss on multi-mode MIMO communications beyond beamforming. In this keynote, we will revisit the fundamentals of point-to-point MIMO communications and explore the new features that arise when operating in the radiative near field. Our next speaker is a professor of wireless communication at the KTH Royal Institute of Technology. He is an IEEE Fellow, Digital Futures Fellow, and Wallenberg Academy Fellow. He has a podcast and YouTube channel called Wireless Future. Now, he's received the 2018 IEEE Marconi Prize Paper Award in Wireless Communications, the 2019 Eurosip Early Career Award, the 2019 IEEE Communications Society Fred W. Ellisick Prize, the 2019 IEEE Signal Processing Magazine Best Column Award, the 2020 Pierre-Simon Laplace Early Career Technical Achievement Award, the 2020 CTTC Early Achievement Award, and the 2021 IEEE ComSoc RCC Early Achievement Award. Ladies and gentlemen, let us welcome Professor Emil Björnson.
Hello, nice to meet you all. So I hope you can hear and see me, and that you can soon see my slides. Is that yes, perfect. So I'm very happy to be here today to talk about one of the research areas that I have been most excited about in the past few years. I mean, as researchers, you always work with a number of different things, but some are close to your heart, and this is one of these areas. So multi-mode MIMO communication beyond beamforming is the name, and I will talk to a large extent about what lies beyond beamforming, and then towards the end I will come into what this means in terms of what I call multi-mode MIMO. So just to recap some of these basic kind of things here. So this whole talk will be about using antenna arrays to do something in communications. And the classical way of using antenna arrays are for two different purposes. One is to do what we call adaptive beamforming, where you can form signal beams focused in different directions. So the antenna array that you are using, putting on your rooftop here, in a, for example, 5G mast, it doesn't have a one directivity, but it can change directivity by sort of sending the same signal from multiple antennas, but with different phase shift. So you get the red beam, the green beam, or the blue beam here bouncing off a building. And we then had the second option, which we call spatial multiplexing, and particularly the gains that can perform. So while beamforming is sort of focusing signal energy so that you get a larger fraction of the radiated power at the location where you want it to be, spatial multiplexing is all about using these three beams, for example, at the same time. So to this device and to this device, we can communicate at the same time, at the same frequency, and if you do it well, they will barely interfere with each other. And this user device here, which is getting two beams, if it has two antennas, it can resolve those two beams, and it can double its data rate or capacity, and here you will have 3 times the capacity than in the best cases, compared to if you want to transmit one beam at a time. And this is what we call MIMO, or multiple input, multiple output. So the multiple inputs here would be the antenna array, so have multiple antennas, and the multiple outputs would be these user devices and the antennas within each one of them. And this is, of course, a known concept for a long time. What became particularly successful in 5G is what we call massive MIMO. And that was mainly about sending different signals at the same time, at the same frequency to many users. So this is what I'm illustrating here, like one beam per user. Maybe we will send 2 beams per user, but that's it. So it's mainly about multiplexing of users. And what I will focus on today is that how we in the future could also use its features much more to send multiple data streams to the same user. So if you have a look at what is it that we have in 5G today, it is this kind of antenna arrays that you see me holding here at the right-hand side. This is a 3 gigahertz band antenna array, containing 32 and 64 antennas. So there are some different options there behind me. These are from Ericsson's headquarters in Stockholm, where I'm working in the neighboring building at KTH. And as you see, it's less than a meter tall and half a meter wide, and this weighs like 12 kilos or something. So it's not something heavy, and it's not something big. So when we say massive, it's only about massive in numbers of antennas. And of course, if you take something like this and put it at the top of a building, as you see here, then even if it's massive in number of antennas, it will look small from the vantage point of the user here down on the ground, which is why forming beams in the conventional way is what we will continue doing in 5G. But what I will focus on in this talk is what might happen if we make the antenna arrays much larger. For example, if we were spread out antennas over the entire building site here. In this case, the array will be large. It will have a large aperture. It will fill up a large portion of your field of view. So as the user, it might then fill up a large angular area. And then we will be operating in something that has to do with the near field. And I think the previous speaker was also mentioning the radiative near field. This is essentially the same kind of things here happening. And what this could potentially turn into is that instead of sending a signal beam, we will focus energy around the user. And more precisely, we might be able to focus multiple signals around the same device. Even if there's no object around that can help us bringing in the signal from a different angle, we might still be able to do a massive multiplexing of signals to the same device, just because we can focus the signal energy very narrowly. So the core of this talk will be to explain to you how this is possible and when it is possible. And as a starting point for that, I then need to begin with saying what is a near field. And we start with a passive antenna, a conventional one. So if you look at electromagnetic textbooks, what the near field and far field is about is what happens when you have a transmitter, which might be physically large. So it has a larger side here, which is called capital D. And then we have a measurement point where we like to figure out how the wave transmitted from this transmitter would look like. And there is a distance, lowercase d, to the measurement point. But if you compare the distance from each of the edges of this big transmitter, well, then there is an additional distance, delta, so d plus delta, the wave needs to travel. And depending on how large this distance d is, there are potential things that might vary. So the amplitude might be different from the edge to the center when measured at this measurement point, because the shear distances are different. So the wave have been thinned out in different ways, depending on how far it has to move. And we also might have the effect that since the distance is different, there might be a phase shift. So the signal that is traveling from the edge will have traveled a longer distance, turning into a phase shift when it reaches the measurement point. And usually it is the phase shifts that we care about. So you might have heard of a number of different distances that have particular names. So we have a transmitter here. We have something we call the Fresnel distance. And here's a formula for this one that depends on the size of the transmitter, the wavelength lambda. And if you are closer than this distance, well, that is when you can see this kind of particular so-called what do you call it? Not radiative, but anyway, we have we have the coupling effect, for example. So when you do mobile payments, for example, then you see this additional parts of the field that are not radiated, but only sort of measured around the transmitter. And this is not what I'm after in this talk. I'm after what we call the radiative near field here, which is also known as the Fresnel region, which goes from this Fresnel distance up to what we call the Fraunhofer distance. And this Fraunhofer distance is usually said to be 2 times capital D squared divided by lambda. And this formula, you find it in all textbooks in electromagnetics. It's seldom really defined why it would be exactly that distance, or strongly motivated at least. You can find motivation like this, saying that, well, for some reason, we would like the waves that come from the center and from the edge, the blue and the red one here, to be reaching the measurement point with a phase difference that is less than the pi rate at the carrier wavelength. Then you can do some math. You can say, well, we can compute the distance difference between the longest path from the edge and from the center. It has a particular formula, the extra path difference between them. You can apply a Taylor approximation here. Find the formula. You say, well, if the this approximate extra distance here is smaller than pi rate when we talk about wavelength, then you get this column for distance. I'm not expecting you to follow every step in this derivation. My main point is that someone said, well, if the phase difference is pi rate or smaller, well, then we should be able to neglect the phase difference. And that turns into this Fraunhofer distance. But it's really arbitrarily selected, and it's not necessary that this is important also in communications when we are interested in data rates and how much data we can transfer over the channels. So if we turn this around and look a bit more from a communication perspective, here's another way of viewing it. We let the transmitter or the measurement point from the previous slide be the one transmitting a wave. And we instead have a large receiver. So now the receiver have a size capital D, the transmitter is a point source. And the red here is going to show you the wavefront of the signal. And now you can see that when the wavefront is hitting the center of my receive antenna, there is an additional distance that I need to move. So, and once again then, if the distance to the center is D, then the extra distance that I need to travel to have a pi rate phase difference, it's the same kind of thing here. The extra distance here would turn into a phase shift smaller than pi rate if the distance to the antenna is greater than D capital F, the Fraunhofer distance. Once again, 2 capital D squared divided by lambda. So this Fraunhofer distance is also appearing in these situations. And this had then to do with whether you can see phase differences over an antenna route. And this is what is going to be important later on. So even if the big wave that you're radiating is always going to bend it, always going to be spherical, well, if you have a large enough receiver, you can still see that kind of curvature. If it's small enough, well, it will look locally plane when you receive it. I was also mentioning amplitude differences. So it might be that the distance to the center and to the edge is sufficiently large in difference, so that the wave hitting the edges have been thinned out more. And one can compute that already when the distance here is like 1.2 times the size of the receiver, you essentially get 92% of the amplitude at the edge compared to the center. So when you are beyond that, you practically don't see any amplitude difference. My point is the following. Consider a typical 5G scenario. 3 GHz band, you have an antenna which is maybe smaller or equal to the wavelength. So say that's equal to the wavelength on the diagonal. That's 1.5 meters. Then the amplitude differences can be observed up to 0.1 meter, 0.2. And this Fraunhofer distance, if you put in the size and the wavelength, it turns into that it's 2 wavelengths where you can observe it. And that is 0.2 meters. So all the things I've been talking about, seeing amplitude differences over the receiver, seeing some kind of phase difference over the receiver, that doesn't really happen in any 5G use case because you will always be many meters away from the receiver. So the whole Fresnel region kind of thing is really irrelevant. But this can change if we start to have physically large arrays. So here is an example of what could happen. So you have once again a transmitter transmitting. I have receive antennas, each of them having a size capital D, but now I have multiple of them. So there's one here, one here, one here, one here, one here, and so on. So each antenna is small, but the total aperture W here is large. So the antenna array as such is large. And I will now mention something that I call the Fraunhofer's array distance. So this is when we are operating in the following case, where we are in the far field of each individual antenna. So the distance to each individual antenna is much larger than this Fraunhofer distance I talked about before. But if you take the same formula and you put in W, the size of the entire array, well, then we are at a distance that is smaller than this Fraunhofer array distance. And what does this mean? Well, it means that every single element will see a wave that looks like it's have constant amplitude, constant phase over the surface. It's like a plane wave coming in. But if you compare the phases or the amplitudes, in particular the phases, between the elements in the array, you will observe the curvature. And this is what helps us to extract additional information from signals. And if I now give you the same kind of example, 3 gigahertz band, 0.1 meter is the wavelength, and I say that I will have an array which is 10 wavelengths for 1 meter long on the longest side, say the diagonal. Then the Fraunhofer array distance, 2 times W squared divided by lambda, becomes 20 meters. And if I make my array 10 meters long, then it turns into 2 kilometers. So all of a sudden, if you make the arrays already in conventional frequency bands like 3 gigahertz, 10 meters by 10 meters or something like that, then you will have a Fraunhofer array distance, which is kilometers. So essentially everything you're trying to serve will be within that range, which is opening up to communicate in the radiative near field. So what does this mean? Well, it means that certain things that we have neglected in the past when it comes to modeling both the channels and what we can do in our communication protocols will change. And we need to have channel models and an understanding of that changes in order to understand what we can do. And we will see that this leads into multimode MIMO communications after a while. So if I now have a transmitter user here, and I have an array here with many elements, these are the black elements, and I have a length cap L here on the horizontal and the vertical side here. Well, if we are computing the conventional far field path loss in line of sight, what we would do is that we will take the total area of my array, L square, and then I will take the area of a sphere with the radius set, which is a distance set here to the center. So 4 pi set square, that is the surface area of a sphere with that side. So the signal is spreading out, it lives on the surface area of a sphere. We compare that area at the distance with the size of the antenna array, and that would sort of represent what fraction of transmitted power we are receiving. So in the far field we can do this because the wave that is hitting the receiver is locally going to be plain, but it's not the case in the near field. In the near field, there are different things we need to care about. We have different distances to different antenna elements here, and these will turn into different altitudes. We are seeing the antenna elements from different angles. That also means that even if the physical size of the antenna is the same, the effective area is different because it looks smaller when you look at it from an angle. And there's also things to have to do with the polarization of waves. The polarization of the wave might be perfectly tuned when it reaches the center of the array, but then it will be skewed when it comes to the edges. And this also needs to be taken into account when you're really close to an antenna array. And in the paper here that you see on the bottom, power scaling laws and near field behaviors of massive MIMO intelligent reflecting surfaces, we obtained this kind of formula, which is telling us more precisely what will be the path loss in free space in the radiative near field. And I'm not going to go into exact details, but it's the same kind of thing here. The end user that transmits is here in the center of the array at the distance set. We have L by L is the size of it. And within this formula, things that are appearing is beta set. This is the far field path loss. But there are also some other things showing up here. There's pi, there's a tangent inverse, and there are some complicated things here. We will use it for simulation next slide. But some interesting things that might happen here is that if we let the distance set be large, what is going to happen is that certain terms here will dominate. So in these cases, the path loss is small. So whenever you compare the path loss to 1 like this, well, then these terms goes away. So here we get beta set over 3. The tangent becomes almost linear, so we can take it away, and we can take away this part here. We get 2 over 3 times beta set. So in the far field, when distance is large, this formula turns into the conventional formula. So we can use this formula both in the radiative near field and in the far field, but in the far field it doesn't provide any additional insights. If we instead let the array becomes very large, we can actually use this formula and let the size, the L, goes to infinity. And if the universe is infinite, well then that's actually possible to essentially build. And one can then show that this formula converges to 1/3. And it's good it converges to something because we can't receive more power than we transmitted. So we need to at maximum get a 1 as the path loss with an infinitely large array. Why don't we get 1? Well, first of all, half of the power goes backwards. We can only capture half of it. That would be 1/2. But why did we get 1/3? Well, we actually lose some impolarization losses when the signal comes in from very weird angles when they are far away. Okay, so we can use this formula. The question is, do we need to use this more complicated formula or not? And when are these phenomena actually appearing? So once again, we have these 3 different phenomena that I was mentioning: different distances, different effective areas, different polarization losses. And here I'm showing you a simulation where I have a fixed distance, 20 meters, to an array which is square sized. And then I will looking at the diagonal of this array and I make it larger and larger. So I start here at this small array and then becomes larger and larger. And there are 4 different formulas. Or 4 different curves. So the upper curve is what happens if I use the far field approximation formula, the beta that I started talking about. Then if I am considering that I have different distances to antennas, actually when you have a large array, we get a smaller number. And if I take 2 first properties into account, I get an even smaller number. And if I take all of them into account, I get the red curve, which is the accurate one. And you can see that if you have really large arrays, you need to take all of these properties into account. Otherwise, you are overestimating how good the array is going to be in terms of capturing energy. But at short distances, it doesn't really matter. And when do we actually start to care about these things? Well, that is when the diagonal is roughly half of the distance to the array. And this is something that we have started to call the Björnson distance. So it's when the distance to the array is equal to 2 times a larger dimension. That is when things are starting to change, but we need to take these things into account. So what does this really mean? Well, it means that when you are in the radiative near field, things will change. You will need to consider your performance differently and also how you're operating your system differently. Here's another way of looking at that. You have an isotropic transmitter. You have an antenna array here containing multiple elements. And what we will have is a length here, which is, I have the diagonal of each element is d. So this side here is square root of n, the number of elements that they have, times d over square root of 2. So this is the length by the length. And the first thing to care about is whether we can beamform signal energy so as well as we can do in the far field, so that we can get the same array gain, the same amplification as we will have in the far field. And we will see a ratio between the actual channel gain that I can get divided with the channel gain that I could ideally get in the far field. And there are 2 different distances that I mentioned so far. One is the Fraunhofer array distance. And if you do the math in this case, it turns into this formula, 2n d squared over lambda squared. This is because the diagonal here is square root of n times d. And this is actually n times the Fraunhofer distance of the individual elements. And then I was talking about the Björnson distance, which is 2 times the diagonal here. So 2 times d times square root of n. And what I'm showing you here in this formula, in this graph, I mean, is this ratio between the actual channel gain and the far field gain. On the vertical axis and on the horizontal axis, different distances. 1 Fraunhofer distance of the individual element, 10, 100, 1,000, and 10,000. So these are then in logarithmic scale showing what kind of result we're getting. And I'm considering a 100 by 100 antenna array with a diagonal which is equal to the wavelength. And you can see that when you are very close, you are having a much smaller antenna array gain than you would have in the far field, simply because you're essentially very close to one of the antenna elements and the other ones are not contributing. Then when you are increasing in distance, eventually you are reaching the Björnson distance. At that point, you are actually getting like 90% of your array gain that you get in the far field. And beyond that, well, you get essentially the same thing as in the far field. Here is the front of array distance. And what I would say is that the front of array distance doesn't really say much at all about what gain we're going to get. That is what the Björnson distance is telling you about. So if you are beyond that distance, you can get all of the gain from the antenna. But there are other interesting things happening that has to do with the front of array distance. So if you are beyond that distance, you can transmit your signals and receive your signals as if you are in the far field. So you can count on that the waves will be flat. And you can use things like array response vectors or the code books that you have in 5G, which is presuming that you will be in the far field. So what will we do if we are at shorter distances? Well, what I showed on the previous slide was that we can, between the Björnson distance and the front of array distance, we can get the same gain as in the far field, but we need to pay attention to how we achieve it. We need to use the spherical curvature to do the beamforming properly. And with code books in 5G, you won't do that. But if you are using uplink pilots and estimate the signals, for example, all the phases, then you will do this automatically. And here is where the interesting thing starts to happen. So if you have a transmitter sending a signal, you're focusing it at the point where the user is. Usually, we say that at this distance, there will be a beam width. So the signal spreads out, but it has a particular focus point and a particular beam width that you can have perpendicular to the direction where the signal is propagating. And the beam width, you can get different formulas. If you talk about angles, then here is the formula, which is inversely proportional to the front of array distance. So you can find that formula here. The interesting thing here is that we usually talk about the 3 dB beam width. That is where the angular window where you can be and still see the same amplification as you would get at the focus point down by half, or 3 dB. The new thing that happens in the radiative near field is that we also have a limited depth of focus. So usually when you focus a signal at a point, the signal continues behind you. But that doesn't need to happen in the radiative near field. And in this paper, a primer of near-field beamforming for arrays of reconfigurable intelligent surfaces, we are computing this formula here, which tells us that when you're focusing the signal at the point distance f, at the user device there, then you will have a depth of focus in 3 dB terms. That you had the ideal, strongest focusing at the focus point, and then it starts to be focused at the distance which is computed like this. You take the front of array distance, take the focus distance, you divide with the front of array distance plus 10 times the focus distance. And then it ends behind you at the distance which looks the same. The formula is the same, it's just a minus sign between these things. And of course, if the front of array distance is equal to 10 times the focus distance, then you get divide by 0 here, and that is when this should be replaced with infinity. So at distances that are shorter than the front of array distance divided by 10, when the focus distance is like that, well, then the beam will end behind you and doesn't continue towards infinity. So here's another illustration of that. Far field versus near field beamforming. So if you're focusing at the device far away, at a distance that's longer than the front of array distance divided by 10, well, then the beam actually starts at the front of array distance divided by 10, and then it continues forever behind you. While if you're focusing the signal at where you are in the radiative near field at close by distances, well, then it starts not by the array, but before it reaches you and ends after, and it doesn't continue towards infinity. And this front of array distance will depend on the wavelength and the size of the array. So if you keep the array size fixed and you are decreasing the wavelength, well, then the front of array distance will become further and further away. then you will be more and more in this field. And if you keep the number of elements fixed and you are changing the wavelength, well, then instead the distance shrinks. But usually we try to keep the aperture, the sizes fixed when we are changing wavelengths. So this will mean that as we go up in frequency, we'll be more and more in this relative field. Here's another illustration of this. So we are considering different distances here. We have a transmitter red here, and we are sending a signal towards the far field. And I have logarithmic scales here on the distance. So 10 Fraunhofer distances, 100, 1,000, 10,000, 100,000. So that is why it looks like the beam here. So the focusing is where we have it yellow. This is where you have a strong amplification. So this is essentially the fraction of the far field focusing that we are getting. So you can see that far away, and in the center where I'm focusing, I get a strong focusing, and elsewhere I don't get it. And usually you should see that you have a sort of beam width which is fixed in angle. And we actually have it here. It just looks like it spreads out because of the logarithmic scale. If I am, however, focusing at the point which is nearby, in this case, we are focusing here. If I need to actually zoom in to see any amplification at all. If I zoom in, I get the small region where I have a strong focusing, and elsewhere I don't have any focusing at all. So it really shows us how we can focus energy from a large array in very tiny regions. So how tiny can those regions be? For example, in terms of beam width. Well, before I was showing you in angles, we have a particular beam width, and there is a classical formula for that one. It's approximately this 1.77, and we have the square root of the wavelength, and we divide with the square root of the Fraunhofer array distance. But we don't usually care about the angle here, but the actual physical distance. Is it large enough to capture an entire antenna or entire tubes device? So what I will now compute is how large or wide will the beam width be when you are at the brink between the near field and far field at the Fraunhofer array distance divided by 10. So then I take the angle here and I multiply with that width, and I get this formula. And what you can see here is that it is not going down with the Fraunhofer array distance, it's going up. So the more you are pushing the far field further and further away, the wider the beam will be where the far field starts, even if it's narrower in the near field. So here's an example of this. I have a antenna array here, which is some wavelengths long here. And these are my 10 antennas. And I'm focusing at the Fraunhofer array distance divided by 10. And the coloring here is telling me that I have a focus point here. There I get the full array gain. And you can see the array gain get another points down to 3 dB or 0.5. And you have a particular beam width here at different distances, but around the focal point is the distance. If I make my array longer, so now it's between 5 and -5 wavelengths here, so it's 10 wavelengths long, my distance to the Fraunhofer array distance divided by 10 moves to the right here. So now it's at a larger distance. And if I keep the same width here as here, you see that actually the 3 dB beam width becomes longer. So we actually are not shrinking the size of the focus area when we are making the array bigger. It's just that it's closer and closer, you see the same kind of width. And why would this be interesting? Well, the question would be, if you are really close to the array, how quickly do you need to change your beamforming? If someone is just moving around the array, will this become, or moving around the use device, will you have to re-estimate things all the time? Well, fortunately not. You can do some math. We did it in the paper. I will not bore you with this, the details. The main thing is that if I have M antennas, I can get the focusing gain proportional to M. And if I move a little bit, I will lose part of it, and I will lose half of it when I move sufficiently long. And in the worst case, it can never be longer than a quarter of the wavelength. So you can never get if you're very close to an antenna array, as I'm here, just 2 wavelengths away from the antenna array, well, then we still have a focusing with the beam width, which is like 4 wavelength, a quarter wavelength wide here. So the focus area will never become super small. It always have a minimum distance. Okay, so I've been talking for a while now, but I was supposed to talk about multimode multiplexing, and that is what we now are ready to talk about. So when we are communicating to a user array, usually we are in this situation. You have a transmitter here, you have a receiver here, you have a beam width, which is sufficiently large so that when you're focusing in a line of sight scenario, a signal towards this receiver, then the width is so large that it captures the entire antenna array. And therefore we can only transmit one signal because all the signals will have the same amplitude, the same phases. When it comes in here, at least it will look like a planar wavefront, and we cannot resolve more than one such signal at a time. If you have dual polarization, you can actually have 2, but let's ignore that for the moment. If you take now this blue receiver and you move it much closer to the receiver, all of a sudden the beam width will become so small that it doesn't capture or cover the entire receiver. And this will now, in this radiative near field scenario, allow us to send multiple signals that are resolved by this array. And these are the spatial modes, multiple signals that we can resolve at receiver. And let me be more concrete. I would consider 2 antenna arrays, 10 by 10. So in this case, I'm still considering a far field scenario, line of sight to the top example from the previous slide. I have 10 antennas here, I have 10 antennas here. So they are half a wavelength space from each other. And the distance between them is now like 700 wavelengths. So they are in the far field. And what you can do in this scenario, free space far field, you can compute the distances and the amplitudes between every pair of antennas. So you get the amplitude and phase shift. You can create a channel matrix. And then you can apply what we do in MIMO communications. The capacity is achieved by something called SVD precoding, or singular value decomposition. And if you compute that singular value decomposition, you will see that almost all of the energy appears in one eigenvalue, one eigenmode. And that's what we talk about modes. And the way of transmitting that is corresponding to that mode is to, you can see that I only have 20 wavelengths here and 750 wavelengths horizontally. So that's why it looks like this is a super wide beam, but actually it's just, we focus a beam towards the receiver here. That's what the blue colors are showing. And then there is nothing to the sides. So you focus the signal energy, you cover the array with one beam, and that's why 98.4% of all the received energy will be going for this mode. There are 1.6% of the energy coming from another mode. How would you reach the receiver in that way? Well, you are beamforming in directions to the sides, which are not actually reaching the receiver in a good way. That's why you get a small energy. But the side lobes of your signal still becomes resolvable at the receiver, and that's why you can get the other 1.6% of energy. There's also an additional 8 modes that you can observe, but all of them move very weak. So we don't need to care about them. All of the energy is essentially in mode 1. So this is what we mean when we say they have a rank 1 channel in a far field. But if we now take the receiver and we move it much closer, and I also, actually in both cases, it was rotated slightly like this. Now it is 7 wavelengths away from the array, and each array is 5 wavelengths wide. In this case, I compute the channel matrix in the same way. Take the amplitude and the phase from the distances. And I compute a singular value decomposition, and I figure out that the strongest way of communicating will result in this physical transmission. So you see I'm focusing somewhere here towards the lower end of the array. And in this way, I can resolve a signal containing 30% of the received signal energy. There is 4 additional modes. One where I'm transmitting a signal towards the upper part here. Then I'm transmitting towards the edges of the array, and then even further towards the edges of the array. And you can see that mode 1 contains 30%, this one 28, this one 24, this one 30%. And that adds up to, I think, 95% of all of the energy here. So I have 10 modes, but the 4 strongest one of them contains 95% of the energy. But the main point here is that we can actually send 4 signals in line of sight, no objects around us, 4 signals at the same time. And by just letting the arrays be large, we can resolve this 4 signal and get 4 times the capacity, because these different modes can resolve different signals at the same time. So what can we fundamentally do if we have big arrays? Well, there is a nice theorem from this paper here, which says that a large antenna array can resolve pi signals for each segment it has within an area of lambda by lambda, so the wavelength squared. And what does this mean? For example, you have an example I'm showing here. We have a big array, which has a length L and a height H. Well, you take that area, L times H, you divide with lambda square, so you figure out how many segments do we have of that area, and then you multiply with pi. This is the number of spatial modes that a big array like this can resolve. And then some of them will be usable by this user device. So in this type of array here, 10 by 30 meters, 3 gigahertz band, as I was considering before, this array as such can resolve like 100,000 different signals. And a few of them, depending on how close you are, will be resolvable for each device, and the other ones will be to serve multiple devices. So my point here is that we are very far from the limits, and so the richness of the channel will be key here in order to figure out how many users we can serve in general, and for each device, how close they are will determine how many modes we can assign to every user. But we have a huge number of modes that is out there in the radio to near field that we can utilize for communications. And before I end, I would like to provide you with some kind of analogy to computing. So in high performance computing, we over time used to increase the clock frequency. So you can see here we went through megahertz ranges, and then we reached like 1 gigahertz around year 2000, and then we started to saturate. So we were not improving the computers anymore by getting a higher and higher sampling rate or clock frequency. What did we do instead? Well, we started to eventually use multiple cores instead. And that is what is the main thing now. If you buy a new computer, you want to have more cores, and the clock frequency will still be a few gigahertz. So what is the point here? Well, in the past, we were chasing higher and higher clock frequencies. And nowadays, we are chasing more and more cores, and we do multi-thread computing. And in communications, I believe this is going to happen soon as well. So in the past, we have been chasing more and more bandwidth. So we went from 20 megahertz in 3G or in 4G to 100 megahertz now in 5G beginning, and then millimeter wave will come along. And after a while, we will then have so much bandwidth that we are not needing that anymore. And the alternative will be more cores, or in our case, more modes. We transmit the same signal at the same frequency, and we get the opportunity to transmit many signals at the same time. So reaching the conclusion that when you are having physically large arrays, you as a user will be in the far field on the individual elements, but you might be in the near field of the entire array. So you are beyond the Fraunhofer distance of the individual elements, but you are below the Fraunhofer array distance divided by 10. And this is where the finite depth beamforming is showing up. And if you are beyond the Björnson distance, you can get the all of the amplitude of the signal, but you will get different phases, and that is what allows you to do what I call multimode multiplexing, where the signals are both limited in beam width and in beam depth, and you can resolve multiple of them at the same time at the same device. And I believe that this might be the new way of increasing the data rate of our device in the future. Instead of chasing more and more bandwidth, going up in frequency more and more, we might be able to use these multiple modes instead in order to communicate more and more data to our devices. So with that, thank you very much for staying all the way until the end of my talk.
Thank you so much, Professor Björnson, for that presentation on multi-mode MIMO communications beyond beamforming. And of course, after that presentation, we'll now move on to the question and answer segment. I believe we have a couple of questions already from the audience, starting with this one. Will it be feasible to deploy large antennas over the entire building walls in terms of cost and power consumption? Prof, what do you think?
So I think that economics is always important. But at first, I think as a researcher, we should figure out what would be fundamentally good with the technology, and then if something can improve things a lot, well, then eventually we will find economics to solve it. But I had this example where you can resolve 100,000 modes. So probably in the near future, we will only need 1,000 of them or 100 of them. So then you don't need to put antennas everywhere. Maybe a few antennas. The important thing is that they fill up the facade of the building, but not that they are half a wavelength spaced. They could be longer distances between them, for example. And I think that we should not build this very expensive industry-grade antenna arrays as we have today, but more think about that, well, the radio chip in a mobile phone is not something that is particularly expensive. So we should build on that type of technology instead.
Thank you so much, Prof, for addressing that question. We have another one from our audience right now. And this next question, Prof, is: the technology that you describe seems to require many antennas in the user device. Is that possible in practice?
That's a good point. So, I mean, looking again at an antenna in your phone, you have a certain area. So that one is given by you. And if you apply that formula to have, take the length times the height, you divide with the wavelength square, that tells you how many modes your device could consider. And when we are moving up in frequency, you can squeeze in many more antenna elements into it. And that is what we already see with millimeter wave. So in millimeter wave iPhones, for example, you could have 16 antennas. So you could essentially resolve 16 signals. Then the channel might not be rich enough for that. But I think that in millimeter wave, we will be able to have a decent number of modes per device, enough for our purposes.
Thank you so much, Prof, for those insightful answers on antennas. We have another question coming in, and this one, Prof, is: in order to increase capacity for multi-users, your idea is to reuse same frequency for different users at different beam directions? How do you take on this question?
Yes. So that is sort of the what we are seeing now already with 5G, that there were sort of two competing developments. One was to continue using mid-band frequencies and use massive MIMO with 64 antennas. The other thing was millimeter wave, which is providing you with great bandwidth. And both of them, I mean, if you have 10 times more antennas or 10 times more bandwidth, both of them can increase your capacity of your network by 10 times. What did the operators start with deploying? Well, they started with the massive MIMO in the conventional bands, because you're reaching your coverage area in a much better manner. So that is what I'm building on here. The idea that if that was what was the most successful thing so far in 5G, and then when the number of users is increasing, why not increase the number of antennas proportional to that, so that we can deal with the signals once again by sending beams to different users instead of having a large amount of spectrum that we need to share.
Thank you so much, Prof, for expanding further into that question. Our next question is: any thought on simplification of multi-mode selection and beamforming weight computation, especially due to SVD?
Yes, so this is a great point. And I think this is where a lot of people are doing research in this area as well. So when it came to massive MIMO with 64 antennas, people said, oh, the complexity is going to be too large. That turned out to not be true, but eventually we will hit that limit. So, and I think an SVD operation here will probably be cubically in the number of antennas, or at least antennas square times users. So what we need to do then is probably to do some smart pre-processing. And a lot of people try to figure out what kind of modes one should consider. If you have, you make some kind of code book of potential modes, considering different angles, different distances, then you take your received signals, you filter it using that bank of digital filters. You try to figure out which of these predefined modes that are actually being utilized for the moment, and then you use them. So you don't try to compute the SVT and find the optimal way of communicating. It's more like, okay, figure out the angles, and then around that one, I know that the mode should be like that.
Thank you so much, Prof, for that deep thoughts on that question. We have another question that seems to be related. It's also about multi-mode, and it says, can multi-mode multiplexing be realized using distributed massive MIMO? What do you think?
Yes, so in a way, this is what distributed MIMO is also about. We haven't looked at as much about that. So in a way, when the antenna array becomes very large, in a way, one can also consider them to be distributed. And why put them on one building when you can put them at different buildings? And yes, these modes are out there. So if you look at it from the user device perspective, again, you can compute how many modes it can resolve, and then you will like to be able to transmit to it so that it fills in all of those modes. And probably some of them will come from the other side, from the front, or some from the back. So if you have arrays on both the front and the back directions, well, then you will be able to use more of those modes. Sometimes the propagation environment around you helps you by letting the signal bounce off objects, and then you can also get all of those modes active. But yes, distributed arrays is even better.
Thank you so much, Prof. And I got to say, our audience is really participative this afternoon here. And we've got another question just come in, and it says, an alternative way to increase the data rate per user is to use more spectrum in terahertz bands. What makes multi-mode MIMO a better solution? How do you address that?
Yes, so the problem with the reason that we go up in frequency, millimeter wave in 5G, and then potentially terahertz bands or sub-terahertz bands in 6G, is just to find more bandwidth. But the problem is that the propagation becomes much worse and worse. So it's only a line of sight scenarios where that will provide much gains. And you even have all of the difficulties to even sustain the link budget because the radio hardware needs to shrink so much. So there are all these complications, and we have seen already with 5G that millimeter wave haven't taken off yet. It will probably do it eventually. And if we then go up even more in frequency, it will be even more challenging to find use cases where it works particularly well. While this multi-mode things, you can use it at conventional frequencies to some extent, at least, and you can at least use them very, very, very well in the millimeter wave band that we talk about in 5G. So I think the number of locations that you can cover with one antenna array will be many more, and which will make it much more convenient to deploy things in this way compared to chasing more and more bandwidth instead. So that is what I wanted to say with that analogy to computing, that in a way you would love to have more and more bandwidth, but if the price to pay is that the coverage range becomes very bad, the power consumption becomes super high, and the things becomes hot, and you are only in a few cases see the actual gains, then you should look elsewhere. And I think multi-mode MIMO is that alternative solution for the future.
Thank you so much, Prof, for that comprehensive answer. And there seems to be just more interest in the audience in this presentation. There's another question that just came in here. It says, can these new MIMO methods also be used with intelligent reflecting surfaces? Can they?
So As people in the audience might have noticed, some of these references that I made to some of my own works were mentioning reconfigurable intelligent or intelligent reflecting surfaces as well, which is also about using big surfaces, but not for transmitting or receiving, but reflecting signals. And when using large surfaces in those scenarios, one should also study these kind of near-field effects. Then I think it's more unclear whether one can create many modes using those big surfaces, because the problem is that every element needs to have one configuration in such a reflecting surface. It's changing the phase with one value. And if you should create many modes or control many modes, you would like to change the phase on a per mode basis. So I unfortunately doubt that one can get all of the modes out of it in a good way, but one should definitely study the near field behaviors of these big surfaces because they are supposed to be big.
All right, and of course, that was our last question. Thank you so much, Professor Björnson, for that comprehensive discussion on multi-mode MIMO communications beyond beamforming. Thank you so much, Prof. Now, this afternoon has been a really enlightening voyage into the future of wireless communications, which will continue with a session on localization of things in beyond 5G ecosystems after a short break to refuel before we continue again. Do be back here in about 15 minutes time at 3 p.m. Singapore time. See you at 3 p.m. And welcome back. Our next session will focus on the localization of things in beyond 5G ecosystems. Now, this keynote will address or discuss the limitations of traditional positioning and move on to the key enablers for high accuracy location awareness in 5G and beyond 5G ecosystems. And to tell us more, or should I say to tell you more about the speaker, he is a professor and founding director of the Wireless Communication and Localization Networks Laboratory at the University of Ferrara. He received the HDE Pushkas Tivada Medal, the IEEE Communication Society's Stephen O. Rice Medal in the field of communications theory, and the IEEE Communication Society's Fred W. Ellisick Prize. Now, he served as editor for IEEE journals, as well as chaired international conferences, and he has been elected chair of the IEEE Communication Society's Radio Communications Technical Committee, and is a co-founder and elected secretary of the IEEE Quantum Communications and Information Technology Emerging Technical Subcommittee. He's an elected fellow of the IEEE and of the IET, and has been selected as an IEEE Distinguished Lecturer. Ladies and gentlemen, let's welcome Dr. Andrea Conti.
Thank you for the kind introduction. I hope you can hear me and see me well. It's a great pleasure to be here. So thank you also to the organizer for the kind invitation. It's really a pleasure to be part of this workshop. So yes, today I'm gonna talk about localization, and in particular localization of things. I hope at the end of this talk you will get excited about this area of research, and if you are a student would like to know more about it. And I will show you how localization of things is so far treated in the 5G ecosystems and what we can expect for beyond 5G ecosystems. So there are a few keywords in the title already: localization of things, 5G and beyond 5G, and ecosystem. And I hope that I will be able to touch base upon this aspect during the talk. Yes, I'm located at the University of Ferrara, and what you see at the bottom of this slide is the profile of a middle-aged castle in the center of the city. So location awareness. So we all know that localization is becoming more and more important. We are now in the technological era where We use since already 3 decades satellite systems, starting from GPS in some part of the world, and now globally the Global Navigation Satellite Systems, GNSS, from through a constellation of satellites that send signals and an evaluation of the time difference of arrival at your GNSS devices is possible to know with a certain level of precision where you are. And this was initially thought for the localization of people or people inside some vehicles. And we will see that nowadays this is not enough anymore in terms of performance or in terms of needs for the new location-based services. And in fact, since we are in the era of the Internet of Things, we want to move toward the localization of things, which is the process of locating, tracking, navigating any possible collaborative or non-collaborative nodes. Nodes can be people, nodes can be objects or vehicles. Collaborative and non-collaborative means that these nodes are willing to participate into the localization process, so they want to exchange messages, measurements, observations with the network to be localized. Someone call it also active localization, while there is also the other important aspects related to the non-collaborative nodes, where the nodes not necessarily want to be localized. The network needs to know where they are, and so this we will see is inside the framework of device-free localization. And to reach the goal of localizing the things, we can use global networks like GNSS or cellular, dedicated network like wireless sensor networks. There are some technology that we will briefly touch upon. And also use a resource of opportunity, which means signals that are already on air for other purposes, for example, for communication, and try to exploit them also for localization, even if they are not designed or they are not thought for this localization purpose. Location awareness is a key enabler for a myriad of new applications. Just to give you a few examples, in the Industry 4.0, where there are cyber physical systems that need to be controlled and maneuvered based on where the good which is manufacturer is, and most of the time you need to know the state of this object under manufacturing quite precisely, also in terms of precision. So we really talk about high accuracy precisions, sometimes even a few millimeter or centimeter. Or in Agriculture 4.0, where you don't need that level of accuracy maybe, but it's important to know where sensors that are on the field capture information about the temperature, acidity, or other chemical quantities that are in your terrain, so that one can go and optimize the resources to increase the efficiency of your agriculture. And this is the concept of Agriculture 4.0. But location awareness is also very important for drone delivery, for example, or for drones used for safety purposes, because to control the drone, we want to know where they are precisely. Definitely, localization is a key enabler for autonomy. We can think of autonomous vehicle. In fact, ETSI has a standardized different level of autonomous vehicles. And we are all used to drive cars that have radars in the front, in the back, just to know if there are obstacles at a certain distance. But if you think in the future that you want to coordinate different vehicles that want to move in the space, you really need to know with high accuracy, few tens of centimeters accuracy, where they are located in space, as well as AGV. AGV are automated guided vehicles in industries, in factories. So robots that move into automated factories. as well as for tracking, accounting, and monitoring flow of people so that are moving in big spaces like airport or malls. Is important to extract these types of analytics based on also on the position. So where the people are, how many people, and how flows of people move for different purposes, from advertising to safety into those environment. And also for digital humanities. I'm from Italy, so allow me to put a few images from Italy, and augmented reality and virtual reality for museum are already a reality. If we are already present, and if we want to increase the level of services to people that want to access virtually some information of these archaeological sites or museum, is important to know with a high level of precision where they are. As well as for any distributed inference or environmental monitor application where you have heterogeneous sensors that collect informations and information that needs to be processed. And if we want to process such information, we also need to know, depending on application with certain level of precision, where the information is coming from. So these heterogeneous sensors that are moving in the space need to be localized so that the information that they send become meaningful, and many others. So just to give you a few preliminaries about 5G and beyond 5G localization. Localization is so important that the 3GPP, who is providing the technical specifications and technical reports for cellular system, define 7 levels of service requirement, which you can see in this table. You see in the first column 1 to 7, and these requirements are given in terms of absolute or relative position, in terms of accuracy, horizontally and vertically, looking also into the 3D network. And we can see that in some cases, the accuracy is sub-meter, from the service level 3 to the 7, we have meter or sub-meter accuracy requirement. Importantly, as well, with the same importance of the accuracy is also the availability, because that level of performance is required to happen 99 or more % of the cases. So your system, your localization system really needs to be reliable. There is also some requirement on the latency that for some level, for some applications is in the order of the second, but in some of them is in the order of tens of milliseconds. So this is where really 5G is needed: latency, accuracy, availability. And you can see the last 3 columns that the different scenarios in which these requirements, service level requirements, are defined. And you can see that the challenges one are also defined for objects or vehicles or people that move rapidly in the space, even on a train, and need to be localized with that level of precision. So current system fail to provide that, or they can provide that in a very limited space where you can build an ad hoc system to reach that level of accuracy. They are challenging. And so what is really foreseen is that there will be an integration of native 5G measurements, the so-called radio access technology dependent measurement, RAT dependent, with radio access technology independent measurement, RAT independent, which are obtained through other technology. That's why we talk about 5G ecosystem. It's an ecosystem of technologies, an ecosystem of information, is an ecosystem of verticals and applications. And in fact, if you look into how the generation of the cellular network progresses over time, we can see that we move from the 2nd generation toward the 5th generation. We are now into the release 17, and discussion are starting by 3GPP, and discussion are starting for release 18, which is what will be called 5G advanced. And you can see that there are RAT dependent and RAT independent technologies, and that the more we move to our newer generation, the more the challenging, the more relevant will be and challenging will be the requirements, and so the more integration is needed. Location awareness is a win-win situation because if from one side we can use all the net resources available in the network, or now we should say in the ecosystem, for improved location-based services, which is using the 5G route-dependent. The 5G new radio measurements could be, for example, time difference of arrival measured from the position of a signal, or could be the angle of arrival. If you have a MIMO or a massive MIMO system, you just hear a beautiful talk about this. Or it can be, or one can also use resources or measurement from which are route independent, like using satellite, GNSS, or Wi-Fi that are in the environment, or Bluetooth, or ultra-wideband. Now, ultra-wideband is becoming more and more relevant, especially for localization, because it's for its capability to solve multipath and so provide precise time accuracy, or also inertial measurement like accelerometer and barometer. Okay, so with this measurement offered by the ecosystem, we can have better accuracy in the knowledge of the position of the devices, and this enable new types of location-based services. But on the other end, that's why I'm talking about a win-win situation. On the other end, if we have better knowledge of the position of the nodes, then we can also improve smartly the management of the network. For example, if we know precisely where the nodes are, our beams, if we do beamforming in a MIMO or massive MIMO setting, can be more directed, can be more pensive toward the direction of the receiver or the transmitter, for example. And this, of course, improve the efficiency of the network, as well as reduce the electromagnetic pollutions in areas where this is not needed. At the network level, for resource allocation, we can allocate better the resources of the network if we know where our nodes are. For some applications where also latency is involved and we need to decide how to slice our network, which will be possible in a standalone 5G network, then the knowledge of the position also will play, of the nodes will play a role, as well as for controlling and maneuvering what we foresee would be the base station of the future, which will be mounted also on UAV to dynamically allocate the resources in space where needed. So win-win situation. So location awareness is relevant not only for the services, but also for the network management. So the network for the localization for the network. And the cycle of location-aware networks that we are interested in is depicted in this figure. Sometimes you will see at the bottom of the slide some reference from which the concept is described, or from which the figure is taken. And we first are interested into the theoretical foundation, what is the best that we can do in a certain environment with a certain technology, and then based on that, we have this sort of cycles which include the technology, all the type of measurements, which can be internode if they are radio measurements or optical measurements, or can be intranode, and if we are using some inertial device, plus some information about the environment, how the object move, or if we have a digital map of the environment. And then we have algorithms. Algorithms take all this information and need to do their best to provide you with the best possible accuracy, the position of the nodes. And this will see is an application of statistical inference, which include also, if available, the exploitation of mobility and perceptual models, and the cooperation in space and time, including the fusion of heterogeneous data. And then we have the applications that can be, I already mentioned application, we can add social networking, logistics, safer rescue, navigation in general. So we can classify our networks in different ways, anchor based on anchor free if we have nodes in node position in the network, which will be called anchors because they are used as a reference node in these cases, or in terms of measurement. So we can have measurements of receive power or time of flight of a signal, which tell us from which we can estimate the distance between every pair of nodes, or we can have measurements that can provide us with the angle of departure or angle of arrival of a signal, so angle-based localization, or we can have measurement that tell us if the object is in proximity of an anchor. For example, if you use Bluetooth, you mainly know that you are within a certain distance from your anchor. Classification can also be done in terms of technology. So in addition to the server network that we will mainly talk about and GNSS that I already mentioned, there are also some local technology that can be used. And if we want the best trade-off between accuracy and coverage, we really need to exploit, as you can see in the bottom left corner of the figure in the bottom, you can see that we need to really exploit the integration of 5G with ultra-wideband and wireless LAN and RFID in some cases, because none of this technology alone provide the required service level. So it is an ecosystem because it's needed of integration of heterogeneous technologies for seamless localization. Ultra-wideband is playing an important role wherever it is needed a sub-meter accuracy. In fact, the main manufacturers are now implementing ultra-wideband chips for precise time of flight estimation in the devices. And 3GPP, as I was mentioning, has envisioned the integration of radio access technology dependent and radio access technology independent measurements for achieving the goal of localization. And localization is a statistical inference problem where we start from a space of observation that provides us with measurements. Some prior information can be about the mobility model, for example, or the dynamics of the object, if it is a prior knowledge, or can be the digital map of the environment in which we are moving. And the algorithm needs to provide us with location estimate. And on the right side of this slide, you see a pictorial view of the localization process where we start from technologies that offer us measurements, receive signal strength indicators, time of arrival, time difference of arrival, angle of arrival. These measurements are affected by uncertainty, of course, and algorithms need to do the best to take the positional information inherent in this measurement and offer to the position-based application the best possible location estimates, and has to be robust with respect to the inaccuracy. They might exploit memory if there is a temporal cooperation, and might exploit spatial cooperation with other nodes. For example, the concept of spatial cooperation is becoming very important in release 18 of the GPP, where manufacturers are talking about side link and the real exploitation of side link. Side link is there already since many years, but none of the operators want to really use it. Now there is some movement because the benefit of the cooperation among nodes is becoming more and more clear. Okay, talking about data fusion, so we want to fuse heterogeneous measurements, and I will be talking about a probabilistic approach, which is called soft information approach, and we will see how inherently such an approach will be able to learn from the environment, the conditions that are present, for example, line of sight or no line of sight condition that really affect severely the performance of the localization, and can exploit a different type of measurements in time, angle, or inertial measurement, as well as different contextual information. Before we talk about this probabilistic approach, I would like to mention that the localization can be active or passive. So when the nodes collaborate with the localization process, we have exchange of measurement with our node. For example, from our base station, our GNB, to our user equipment and vice versa. But there are also situations in which nodes do not collaborate or are not equipped with devices, but still it's important for the network to know if there are moving objects in the environment, for example. In such a case, we talk about device-free localization. We also talk about passive localization from the point of view of the source, if rather than using dedicated signal for localization, one exploit signals that are already on air for other purposes, for example, communication. And in such a case, we talk about signals of opportunity. Okay. We are in a framework for device-free localization, and we are in the framework of sensor radar networks, where we have node that transmits, node that receive, and the position of such nodes is based on information extracted from the waveform that these nodes reflect. So we need to be able to extract information on the position of the target in the sensor radar network setting. The object that we want to localize are called target, and we need to be able to localize this target based on information that we extract from reflections of the waveform. So this is challenging because any object reflects electromagnetic waves, any furniture, any door, any person which is in the environment reflect. And so we will need to be able to remove these impairments, which is called clutter, associate components of the received reflected signal to each target, and based on this associated component, look into micro variation of this component and understand, try to estimate where the position of the target is. So the localization in the 5G ecosystem, I hope I was able to clarify already that is pretty broad in the sense, active, passive, with using different type of measurements, is an ecosystem that integrate and fuse different type of data. And to satisfy the challenging service level requirement, classical methods typically fail. And what are classical methods? Classical methods are what the so-called single value estimate methods, where based on the measurement of time, or based on a measurement of angle of the path of arrival, or based on an estimate of the power, measurement of the received power, one determine what is the distance between a pair of nodes, typically an anchor and the agent or the target, and then using also some prior information if available, the localization algorithm provide us the coordinates of for the positional state of the node. This is an approach which is similar to hard decoding, if some of you is familiar with coding theory, where you, rather than using all your sample, you make a decision on what was the received symbols and bits, and then you decode. And of course, this choice requires some quantization early in the process, and quantization is always loss of information. So this is not this classical approach. This is why classical approach fails, in addition to the fact that they are not able to take into account often the condition, the propagation condition in the environment, for example, line of sight or non-line-of-sight, that severely affect, in addition to multipath, the estimation of the time or the angle of arrival. So recently it was proposed a new approach, which is a probabilistic approach, which is based on soft information. So rather than making a decision of what is the distance, what is the angle. Every time we receive a measurement, we built a probabilistic description of what the distance could be, what the angle could be. And this has some significant benefit because it's more robust to detrimental effects like multi-pattern minus-time side conditions. It also allows for easy integration because this can be done independently of what the measurements are. And it can also is a system. We will see that is a system that will learn the condition of the environment, and that's why it can better exploit the measurements. So some insight. Basically, we are saying that rather than making an hard decision on the time angle based on each measurement, what we are saying is that we keep some probabilistic description of what the time or angle could be. And this is represented by these LY1, LY2, LYN that you see in the right of the figure that I'm showing you now. And those are generative models. Those are functions that describe probabilistically how the measurement is associated with the time, angle, or other features that are related to the positions, okay, probabilistically. So we're talking about estimation of PDFs. And to do that, and of course, the environment are so cumbersome that we cannot assume any analytical model or easy model like Gaussian PDFs pretending that it works in a particular environment, because this is why classical algorithm fail. Rather than that, we need to learn from the environment. So this is where machine learning also come into play. And I will give you some more detail when I will talk about this concept of soft information applied to 5G. And just to give you a pictorial view of what data fusion means and what probabilistic description of the distance or the angle or the context information means, you can see in the right figure now a scenario with the purple contextual information. We know that the two anchors, the red single and the agent, the blue circle, are in a certain environment with that S shape. And for example, from the anchor in the bottom left, we are able to measure times and so distances, and we have a description, a soft range information that describes probabilistically what the distance could be. From the top right anchor, we have a measurement of angle, for example, and so we can see probabilistically what the angle could be. And then the purple is the context. We know that our node is inside that environment. The context could also be a dynamic model, for example. And then, by fusing, multiplying these informations, we obtain in the bottom of this right figure the new soft information, and maximizing the soft information that we see will be basically likelihood in a non-Bayesian setting. We will be able to determine more accurately where the position of the node is. So the workflow is that in an offline stage, we exchange measurements. Measurements are this vector Y. The received signal contain positional information through some features, data, which is, for example, time or angle or any other type of features. The information, the measurement that we take are typically rich. So in some cases, dimensionality reduction, for example, to some principal component analysis method might be needed. And then there is a mapping of the features into and then measurements, which is this F hat, which is an approximation learned from the environment through, for example, supervised machine learning techniques of the relation between the measurements in the reduced space and the features. And then in the online space, every time a new measurement comes, in the online stage, every time a new measurement comes, Y new, it is mapped into the reduced dimensionality space. and we consider the generative model for that specific measurement as our likelihood. So in the 5G setting, just to give you one example, for example, using the positioning reference signal, the PRS, for downlink time difference of arrival. The PRS is defined as an FDM signal dedicated to localization. You can see in the top left the frequency time mapping of this PRS signal, an example of it. And based on this PRS, it's possible to estimate the time of flight of a signal between any base station and the user equipment. And the 5G localization works in a way that is based on time difference of arrival. So the one base station is assumed as a reference base stations, and all the times of arrival are, we take the difference of all the time of arrival with respect to the time of arrival of that specific base stations. Of course, here there is a key important problem of how to select the best base stations, and that works on it. And in such a case, the soft information-based localization approach associate this time difference for a given time difference of arrival, provide the likelihood in a Bayesian setting as a function of all the possible distances between the object in an unknown position P and that base stations. And by multiplying, because this likelihood have uncertainties which are independent, the measurement can also be taken with different technologies from one anchor to another anchor. By multiplying these, it's possible to then apply algorithm like that maximize the likelihood, or that maximize the posterior probability, or that minimize the mean square error, or any type of algorithm can be used. What we see on the bottom right is a representation of two hyperbolas in probabilistic sense. So you see a shape which is not just one hyperbola as in the figure above for single value estimate, which represent two time difference of arrival when anchor one is taken as a reference, and one hyperbola shape is related to the GNB2, next generation base station 2, or GNB3. This also allows to easily perform data fusion, because this likelihood can have any shape based on any type of measurement that we take. For example, we see here an example of a time difference of arrival from 5G on the left with a time of arrival from Wi-Fi, and you see the fusion of the two likelihood. And you want to find the maximum in that blue area on the right. Okay, of course, there is a problem of how to approximate the generative model, so the shaping of your likelihood to probabilistically account for any possible value of the features of the positional feature associated to a measurement, and there are work we've been developing some work. You will see some reference later for how to efficiently do this offline phase and this online phase. Okay, so I think I would like to move a little bit quicker, so I will skip a few slides. I just want to give you an idea on the benefit of the soft information based localization when applied to an ultra-wideband network. For ultra-wideband network, according to the 802.15.4a channel models, indoor residential, the bottom left figure, outdoor, the bottom right figure, you see the localization error outage, which is the complementary cumulative distributed function of the abscissa. The abscissa is the error in the localization, is the absolute value of the difference between the position estimate and the true position. And you see that the more you go to the left, the better it is. And you see that with the same measurement, single value estimate provided the green curve. We have 3 green curves according to the different no line of sight probability. And we move with soft information toward the red curves, which are much, much better. So for example, with only 10% of outage, meaning that the availability of the system with a certain performance will be 90%. In red, we can have a couple of meters, whereas with a single value estimate, we will get 6-7 meters of error. So to analyze the performance in 5G and beyond 5G network within some international project, we've been developing some simulator that is able to generate precisely all the aspects contained into the technical specifications from the signals, PRS, SRS, multi-RTT, to the parameters of the antennas, the polarization, the noise figures, to the scenarios where the GNBs are according to the 3GPP technical specification. We use the quadriga channel simulator. We implemented the waveform processing, and we will be able to show the difference between 5G localization or beyond 5G localization with the classical approaches with respect to soft information approaches. These are some numbers related to the parameters contained in the technical specification. But just to give you a few examples, we are in scenarios for urban micro, the left, and indoor open office, the right, standardized by 3GPP, where you have in a certain environment a certain number of base stations. And this certain number of base stations and this different environment, outdoor versus indoor, provide you different probabilities of having at least 3 base stations in line of sight or no line of sight. Remember, line of sight or no line of sight conditions significantly affect the localization performance, and based on that, and based the soft information has shown that is capable of learning this situation and provide better accuracy. In fact, in the urban micro scenarios, you can see, for example, that while in the technical specification, your empirical cumulative distribution function of the horizontal localization error is given by this symbol, asterisk and crosses, at 50, 60, 70, and 75 and 90 percentile, which provide when the 90 percentile error in the order of 8 meters for urban micro scenario. You can see that with soft information, you can improve significantly performance, and with the same measurement obtain a couple of meters of error at 90%. And we show type 1, type 2 for different configuration of the positioning referring signal. And similarly, you can see the gain, and you basically see how much you move from your symbols to the curves, to the lines toward the left. And you see that there is a significant improvement of the performance by using a probabilistic approach rather than single value estimate. We also show the performance in after this work, which is the review. We also show the performance of localization by exploiting a millimeter wave, so FR2 instead of FR1, and we can see that the performance using millimeter wave in the 3GPP 30 gig standardized scenario is really much improved. There you can also use the angle of arrival and in addition to time of arrival, and you improve the performance and you have sub-meter accuracy. So this shows that it is possible to reach the service requirement asked by 3GPP. And then we were also able to show the improvement of the localization when using or fusing also data from Wi-Fi. And you can see that from single technology, the dash is Wi-Fi only or 5G only, using classical approaches with probabilistic approach, soft information, you improve and you have the blue and the red, and you improve even forward the green curve when you go with the data fusion. Okay, so in summary, soft information approach seamlessly fuse different type of position related measurements, can be easily integrated in 5G architecture and adapted for future beyond 5G networks, and it can exploit different type of measurement defined in 3GPP settings. Okay, so I will. I think my time is now over. I would like just to conclude with a couple of slides to tell you where we are going. In particular, I would like to tell you that if you are interested in localization, the ComSoc has put together a best reading series on network localization and navigation, and this is the link for it. And I hope that you might get interested into this best reading, and feel free to contact me if you have any questions. But what is next? Because I mainly talk about 5G localization, and for some of the aspects like the real exploitation of millimeter waves, we were already in sort of beyond 5G, or let's say 5G advanced, at least 18. But what is next? So what is beyond the 5G ecosystem? So definitely there will be integrated sensing and communication, meaning that we want either to integrate the sensor radar network and the 5G localization together. And this can be done in two ways, as separate networks that fuse the information at a higher level, or by doing the two things really together. So using signaling that can serve for both localization and radar, radar and communication, or localization and communication. So there is the problem of how to jointly optimize the resources. Another aspect is understanding how the multidimensional stochastic sampling is affected by uncertainty on the position of the nodes, and the use of intelligent surfaces to being able to control the reflection of the electromagnetic waves, so that we can improve also the localization in scenarios that are affected by abstractors. And in the near future, after 6G, probably quantum sensing, so exploiting quantum mechanical properties to do a better illumination and a better sensing and a better estimation of distance in position also. So as a takeaway message, space is the next frontier. This is a quote from Star Trek movie, but this was before that a quote by the pioneer of digital synchronization, Dr. Bill Leasy, and at the USC, and basically all the works on MIMO, wireless MIMO, account for it. But if the space is the near and is the next frontier, we really need to know where we are in the space. So location, location, location. And with that, I'll conclude my sharing, and I will be happy to take any question, if any, and I invite you to contact me for further discussion. Thank you.
Thank you so much, Dr. Conti, for that insightful presentation on localization of things. And of course, now we'll move on to the question and answer segment. We have a few questions from the audience right now, starting with this one. Can you tell us more about 3GPP scenarios and localization in them? Dr. Conti, your thoughts?
Yes. So the scenarios are challenging, the requirements are challenging, as I was mentioning. And in fact, for a matter of time, I skipped a short video that shows something that I would like to maybe I can take a couple of minutes to answer this question and show this also by exploiting this video. I think this could be interesting for someone. This is just a guide representation of the work that we've been done on probabilistic approach for localization. And this guy this graphical user interface show is an interface for the core of the method that I propose, but might give a clearer vision of what is the difference of using classical approaches with respect to probabilistic approach. So if you are fine with that, I can show a 2.5 video for answering this question. Can I go?
Sure. Let me just check. There's a 2.5-minute video from Dr. Conti. Can we play that? Are we able to let him play that?
Let's try.
That's
If you can show me that. Okay, thank you very much. So I hope you can hear the audio. I will add a few words in case. So you see on the top left the 3GPP scenario that you can select. On the top right, you see all the characteristics that you can select on the signals. In the top, in the bottom left, you see the soft information and how evolving times, and on the right, the performance. You will see red trajectories estimated in real time, as well as red performances from 3GPP like classical methods, and in blue, the soft information one. So, okay, you see here your green agent, which is moving. You see the red crosses, which are the classical approaches, and the blue crosses are the soft information. So you see that in this case, we are using angle of arrival, and you see what is the improvement of the blue with respect to the red. Now you can see that the shape of the soft information is changed because we go from angle of arrival to time difference of arrival. So now you have hyperbolas type of probabilistic descriptions, and you see what the performance are. These are performance at millimeter wave at 30 gigahertz by fusing angle of departure in this moment and a downlink time difference of arrival. And different type of measurement in the standards can be used.
Thank you so much, Dr. Conti, for that very visual elaboration to help our audiences.
So this is this was. I don't know if the audio was possible to if I shared the audio. So I prefer to talk. I hope I didn't talk on top of it. But yeah, this is just to show you know what happened when you use one approach or the other, and the fact that you move from some meter accuracy to sub-meter accuracy.
Thank you so much. And we've got a few more questions for you, Dr. Conti, from our audience. The next question is,
yes, please.
Can 5G, 6G or 6G localization cover both indoor and outdoor accurately and replace GNSS and GPS?
This is a very important and relevant question, so thank you. Well, this is the goal. This is the hope. We have seen that the service level requirement defined by 3GPP are much better than what you can expect to do with the GNSS, especially because there are environments that are in which GNSS is challenged. But as I try to say, there is no one technology that surpasses the other. It is really an integration of technology. By exploiting data fusion and all these technology, we hope that we can achieve this sub-meter level accuracy in 99% of the cases that 3GPP asks for. It's difficult. It's not going to happen in 5G like this, because there are first of all, the operators need really to unleash all the bandwidth for dedicated signals. Plus, there is the need to develop methodologies for extracting the best out of any type of measurement and fuse them. So the probabilistic approach based on soft information that I mentioned in my talk seems a good way to do this, and this is why I offered this in this talk.
Thank you so much for a very insightful answer. We have another question that just came in, and this one is, can quantum effects be used for enhanced localization accuracy? Can they, Doctor?
Okay, so I'm so glad I received this question, even if I don't have a clear answer. Okay, so I'm I'm working. I start working in my group on this. So I think I have a limited view on this, and I like to give kind of crystal ball answer. But I think they will. You shouldn't expect this in the next decade. So towards 6G, I think it requires more time because we don't have at the moment devices. The world of quantum is mainly related to quantum computing. So far, we are not. We are working for quantum sensing and quantum communication, but there is this concept of quantum illumination, where you emit quantum states, and based on the states, on the discrimination that you can do with the receiver, you are able to understand better, for example, some what happened or which type of quantum channel you have seen, and these include also better estimate, for example, of the distances. So I think that in the future, this is what we are working for. This is where research is starting now, and I hope that many of you will be also interested in the quantum communication and sensing, because it's really something that for your future, in more than 10 years from now, will become relevant. So I think my answer is, I think yes, and this is what I am personally also working for. If this is gonna be really effective on a large scale, like instead the localization with GNSS or smartphone, I think is gonna happen in some decades. It's not gonna be tomorrow. But I think that's a very important and interesting direction.
Thank you so much, Dr. Conti, for addressing that question. We have our next question that just came in, and this is, do you have any comments on the localization with soft information using factor graph for 5G and 6G? What are your comments on this?
Okay, so this is another important point. In fact, there are already algorithms, classical algorithms, that are based on the concept of network factor graphs. Okay, so when you describe your network with a factor graph, but you have the different nodes, and so the point is that these nodes needs to exchange messages. So to exchange these messages can be a representation of the generative model that I was mentioning. Okay, so in fact, the probabilistic approach that I was showing is already kind of related into this question, and already look into the implementation with network factor graph. Network factor graph is there is some interesting work that dates back in proceeding of IWFC 2009, and more recently in the proceeding of IWFC 2019, where the soft information approach was proposed. We have shown also how to implement a distributed localization via soft information, and to do this distributed localization, you can see your network of nodes as a network factor graph that where on each link of the graph you exchange messages which are associated to this likelihood. So definitely yes, they are related, and they can be implemented in this way, as long as you allow side link. So for the implementation to the 5G and beyond 5G, we need the operator to open up the side links, so the direct link among nodes. And it seems that they are convinced about the importance of it. And in fact, in the first meetings of the 3GPP for the release 18, this is one of the 3 key points that is mentioned, in addition to how to use artificial intelligence and machine learning for localization.
Thank you so much, Dr. Conti, for those inputs on that last question. Still have a couple more, and hopefully we can finish all of them. The next question is, can the localization approach you mentioned be directly implemented into 5G architecture? Can it?
Well, In fact, yes. So we are developing these things inside some international project. I can give you a direct example of it because we are exactly working on this. So there is one European project which is called Locus, where we are implementing atomic virtual function and atomic services that are implemented at the architecture level. So we have access to the cloud of an operator and the virtualization of its network, and this algorithm we are implementing into the network, and we are showing how they work inside that project. So yes, it doesn't require any change into the measurement or functions that are already defined in 3GPP, and this is important because we can do application-driven research, but that can be hopefully impactful only if industries and manufacturers and operators then are able to take into account, and to achieve that you need to be compatible with the 5G architecture, and in such a case it is.
Wonderful. I think we can squeeze in one last question just before we hit 4 p.m. Over here in Singapore, and this is this one. Can you elaborate on multi-target tracking with device-free localization?
Yes, and to do this quickly, can you show my slide again, if possible? Okay, thank you. So the point is that you see that you need to be based on the reflected signal. So you have your target that moves in the environment, and you have, for example, a transmitter that emit a signal, and the waveforms are reflected by the target and reach some receivers. And these receiver see waveforms that are varying in time, and based on these received waveform, then one can estimate the position of the target. And in fact, one can also estimate the position of multiple targets. So, for example, here you see a video of a single millimeter wave MIMO radar, and in this video you see 1, 2, 3 persons that enter the environment, and they are tracked applying the method that I mentioned you before into this sensor radar network tracking. So this is just a real-time experimentation. You see the video of the people moving on top, and you see the information which is extracted below. So I hope that this video show a little bit of what you can do for device-free localization. The challenges are that you need to understand which component of the reflected signal is associated to each target, and you also need to understand how to develop methods to remove the reflection for things that are not related to the targets.
Thank you so much. Thank you so much, Dr. Conti, for helping to answer all those questions from our audience, and of course for that intricate discussion on localization of things. Thank you very much.
Thank you. It was a pleasure to be with you all.
Absolute pleasure. And now, for the last keynote of today's session, we will explore deep reinforcement learning for control of large-scale communication infrastructures. Now, this talk will begin with a brief introduction to reinforcement learning, also known as RL, and present the use of RL to train a smart policy for synchronization of domain controllers in order to maximize performance gains in SDN. We'll present a method to decouple actions from the state space for the value function learning process, and a relatively simple transition model is learned to determine the action that causes the associated state transition. Now, our next speaker has been the Tanaka Chair Professor in the Electrical and Electronic Engineering, as well as Computing departments at Imperial College. He serves as the Head of Communications and Signal Processing Group in the EE department at Imperial. He received the Distinguished Member of Technical Staff Award from AT&T Bell Labs, the Royal Society Wolfson Research Merit Award, and became a member of Academia Europea in 2012. and an IET Fellow in 2021. Ladies and gentlemen, please welcome Professor Kin K. Leung.
Hello, I hope you can hear my voice and my screen. Thank you very much for your very kind introduction. It's my pleasure to be here. Literally, I'm hosting some visitors from Singapore, and while I'm connecting to you to give a speech in Singapore here, this is what a coincidence. The world is well connected. Thank you very much for having me here. And I show my first slide. I include our landmark at Imperial College, which is the Queen's Tower. In case you have not visited Imperial, you are invited to come for a visit. For today's talk, I would like to focus on reinforcement learning for control of communication infrastructure. As I shown on this slide, I have a large number of collaborators working with me on this subject, and we like to acknowledge their contribution in the content, to the content of my presentation here. So let me move on. Let me step through. Yes, I would like to introduce a concept based upon software-defined network, which is an extension of software-defined network SDN. Primarily, we introduce a concept called SDC. The SDC is actually can be viewed as just extending the SDN, which is focused primarily on communication. Now we allow to the network to include data servers, data storage, and other resources. So as we understand the concept of SDN, essentially all the resources will be grouped in one domain. This one domain typically belong to the same organization, company, and other same department. So you have different domain of resources, including communications and data servers resources, but domains are connected together to form the network. So as the diagram shown imply here, all the data links connecting different domains together at the bottom here form so-called the data plane. This is the plane, the communication facilities supporting linking the providing transfer of user data. And then the resource will be controlled by, within each domain will be controlled by a controller. So each domain would have one controller like this, and then the controller need to link up among themselves so that they form the control plane. So essentially, let's say for sharing resources across domains, then we rely on the controllers communicating among themselves to coordinate in such sharing of resources across domains, or even for the matter of using the communication resources to support communication. So this is the setting we are considering, because there are a lot of work going on in the industry, in the academia, to work on SDN network, but we are extending beyond just the communication. We consider other resources as well. And the focus here, as our work developed, our focus is to enable all domains, different domains belong to different organizations, kind of join up dynamically together. So, so we have a dynamic situation here instead of being stationary. And secondly, the focus here is to allow sharing of resources across the domains. To support that, then you would expect the controller to have constant communication among themselves to update each others regarding the status of the resource within each domain. Otherwise, we cannot have effective sharing of resources across domain. And so the challenge, one of the challenges we have is we have the so-called controller synchronization problem, which I will discuss a bit more because I would like to use this as an example to illustrate how reinforcement learning will be useful. And we also need to develop sophisticated techniques to allow sharing of resources across domains, because what's the purpose of the SDC, software defined coalition, is to enable different partners, different coalition partners to share resources. So it's not a simple problem, but we need to develop new techniques to support that kind of sharing. And now, as you can see, the whole SDC here is actually a very agile, very dynamic, distributed processing environment, if you can think of that way. It depends on where you are coming from, whether coming from communication perspective or coming from computing capability perspective. Nevertheless, the whole infrastructure can definitely be used to support distributed machine learning, distributed analytic applications. So that is one area we have to consider, how we can make use of such infrastructure to support different kinds of applications. Now, so this is the setting we have been working on, all right? And actually this setting, SDC setting, is not, has a lot of overlap related to the so-called cloud computing, which we are so familiar with. But the emphasis would actually slightly different. For cloud computing, we have the infrastructure at the bottom. We have a platform to support different applications. So we have a lot of end users trying to make use of different apps, different storage, computational capability. And so that is what is cloud computing is all about. And there are a lot of very popular cloud applications like Google Map and Dropbox and famous YouTube, Netflix, and those are applications running on the cloud. But if you look at the relationship between cloud and SDN, essentially you can see there's quite a bit of overlap. Okay, and because cloud can be running on the platform, the network is actually, the infrastructure is actually SDC network or SDN network. So there's a relationship. So we are not, when we deal with the SDC, software defined coalition, is not so different from what we have been using all along. Now, let me come back to the issue to illustrate a little bit about the so-called SDC synchronization, controller synchronization. What are the issues there? The issue is we want to share resources. Let's say I have a user here. I would like to share resources in this domain. So what it means is the controller initially would, each domain has the controller. The controller knows exactly the status of the resources, what resources will be available, what is congested, and how much spare capacity we can share. So each controller knows its own domain. But yet, when I share resources across domain, that means I need some resource in the red domain, but also I need some resource in the green domain as well as the yellow domain. That means the corresponding controller must coordinate, must interact with each other so that to support the sharing of my resources to support my application. Now then it brings the question. The question is the information possessed by each domain regarding the neighboring domains must be updated. If the status information is not updated, there's no way that we can have effective sharing, resource sharing mechanism. So if we have updated information, that means the controller must exchange status information among themselves. However, there's a cost associated with it. The more often we synchronize, then there's the more overhead. then the performance of sharing will be better because we have updated information. The opposite is also true. Then the question is, what is the good controller synchronization policy? Namely, when and which pair of controllers should synchronize their update each other regarding their respective resource status in their domain. And for the given performance metric and some budget, because we can synchronize every single second, at every moment, we can do that, but we have a budget for that. So we have to subject ourselves to develop this kind of synchronization policy subject to our constraint. So this is the problem I would like to use to capture to illustrate how reinforcement learning can be useful. All right, as I said in my introduction, I would like to, the abstract, I would like to give a very high-level introduction of reinforcement learning. And if you look at the reinforcement learning technique, the fundamental mathematical formalization is actually so-called the Markov decision process. So the idea is this: I have some system, I call this environment. This system is very, very general and very flexible. It could be very large system, and it can be only one single computer system, and maybe a very large communication network. But here is the environment. So we have an agent here. The agent can make some observation from the environment. We call this state. Okay, so essentially it's the status of your system, and then the agent would, given the state of your system, of your environment, the agent would select the best action, okay, to take, and then it would take the action and apply the action to the environment. And because of the action is taken, then the environment status will change. The state of the system will change from the current state to the next state. Okay, and at the same time, the agent can receive some reward because of the action taken, given the current previous state of the system. So the idea of the agent is to going through some learning process and trying to learn what action is the best over time, so that I can maximize my long-term reward. So that is what, in essence, what the Markov decision process (MDP) is doing. All right. Without going into the math, this is the fundamental essence of the basic essence of the MDP, and that is the mathematical backing or principle of reinforcement learning. So if you look at reinforcement learning, then you can see it has the learning part as well as the control part, because the learning is to learn what kind of control policy, action policy you should take. Action is control. You want to control something. You want to take some action to control things, and so that's an action control part. But it's also learning. Learning is in the sense that the agent may not know initially how to make decision, how to select the action to take in order to maximize the long-term reward. But it slowly takes some action which may not be optimal at the beginning, but then slowly, oh, if I'm this state and I am taking this action, then I see a lot of reward. That is the good thing to do. That's a good action. Slowly, the agent would learn and acquire that knowledge, and that is the learning part of reinforcement learning. Sounds everything is okay, but then we run into trouble. The trouble is as the system become complicated. Let's say it's a large infrastructure, let's say even within a university setting, you have many departments. They have the computer system. They all talk to each other, share computational resources. You can easily find the so-called the state and action space becomes so large, and because you have so many possible states of your system, and you have so many combinations of states and action pairs, then you can possibly occur. As a result of this large state action space, then it would take a lot of data, and if possible at all, in order to train the agent, because the agent has to learn initially. And so it takes a long time to train. So we have a lot of difficulty in developing the policy when the system is large. There are many possible solutions I list down here, and try to tackle this so-called state explosion problem. And I will go through one or two of them, just to illustrate precisely how we can tackle this state explosion issue. All right, so far so good. So let's move on to go back to our controller synchronization problem. Okay, so let's use a very specific example just to illustrate the point. All right, and then you can see, you can generalize this for other application scenario, problem scenarios you want to apply reinforcement learning to. The question is this, okay? Let's say I need to find a path, a communication path across multiple domains, from domain 1 on the left, all the way going through different domains. And finally, I would like to reach some place in domain 8. So I would like to find a path. Let's say I want to find a path. Let me use different color of pen. Let's say I want to find a path connecting me to here and going through. This is the path I need to go through, and in order to reach from all the way from the left to the right. So let's say I define what's the good path for me. Let's say, so for simplicity, I want to define the number of hops along the path. The number of hops along the path is a reflection of the quality. I want to minimize the number of hops, which is often related to the delay passing through the path. So obviously, as we said, the controller in domain 1 would obviously know exactly all the path stat, all the link status. Okay, and also so is for controller for domain 2. So each domain has the controller. The controller knows exactly the status of each within the domain. But in order to find the best path from domain 1 on the left to domain 8 on the right, we need all the domain controllers to have some understanding of the status within all 8 domains. Otherwise, we won't be able to find the best path. Okay. All right. Suppose then this is where the problem of the controller synchronization. The synchronization is to identify some way the controllers will synchronize with each other. Okay, so that is the policy, synchronization policy we need to develop. Okay, so how can we use Markov decision process to handle that? Now, let's say we define the state. This is the state definition of this system. The state is each state is a vector. Each state is a vector. Okay, in this case, is a vector of 7 numbers. Okay, the number represent. Let's say this is 5. Represent the time elapsed since the last time domain 1 synchronize with the corresponding domain. In this case, 5 means that it has been 5 time units since domain 1 controller synchronized with domain 2 controller. Okay, so 40 here is this, that has been 40 time units since domain 1 synchronized with domain 8. Okay, this is the state of the system. And the action, what's the action? The action is in this time slot, and whenever you see 0 means that domain 1 is not going to be synchronized with domain 2. Okay, instead, in this case, it's a vector, and this one indicating that at this time slot, the policy is to say domain 1 was synchronized with domain 6. Okay, no other domain. In this case, we are subject to this constraint, namely in each time slot, domain 1 controller would only synchronize with one of the remaining controllers, only one. Okay, so this is the constraint we have. And then if you look at the reward, what's the reward? Okay, the reward we define is the reduction of the latency after the synchronization. Because once domain 1 synchronized with the another controller, that means domain 1 would know, let's say domain 6, the most updated link status in domain 6. Then when domain 1 wants to find the best path from 1 to 8, domain 1 to 8, then knowing the updated information would be very helpful. Okay, and then the reward is to reflect the improvement of the latency by knowing the updated information. And then what we want to maximize, we want to maximize the exponential decay of reduction of delay. And that is the formulation of our MDP. Then obviously I would like to highlight here what's going on here. What the situation is, within each domain, there will be some of the nodes are mobile. So the communication links are not up all the time. Some of them would fail, some of them are not doing well, and some links, new link will be set up. So there are a lot of dynamics going on within each domain. And the fact is that the dynamics within each domain would differ from the other domain. Then you can see from here, let's say you can see here is 40 time units. That means 40 time units since domain 1 controller synchronized with domain 8. You would think probably that in the next coming time slot, domain 1 should synchronize with domain 8 controller because it's been 40 time units. However, we do not necessarily need to go with the longest elapsed time, but instead the policy is to say I don't synchronize, domain 1 controller doesn't synchronize with controller 8, instead we synchronize with domain 6. The reason is because of the dynamics in each domain is different. Therefore, even though there's been longest time since the domain 8 has been synchronized with domain 1 controller, but if let's say if domain 8 is very stable, it hardly has any change. It doesn't really matter how much time it has. Okay, it has elapsed since the synchronization with controller 1. So the essence is to let the reinforcement learning to learn the dynamics of the system, because learning the dynamics through observing the reduction of your delay. So then we will figure out, because perhaps domain 6 has a lot of a dynamic situation, then a lot of link changes, a lot of ups and downs within the domain, then domain 1 controller should synchronize with domain 6 more often. So going through the learning would help us to automatically sort out which ones, what's the best way to, which pair of controllers should synchronize with domain, would synchronize with each other. I hope to give you the essence of why reinforcement learning or the MDP would be helpful in this kind of solving this kind of problem. I use this as an illustrative example. You can think of many other scenarios where you can formulate your problem as MDP and then use reinforcement learning technique to solve. It's very general technique. Okay, although I have to say it also has some limitation, but by far it's very applicable. Now, okay, well then we formulate the problem with as MDP. Then we have to solve it. What does it mean by solving it? We have to find the policy, namely for a given state. Okay, what kind of action, given state, and I'm taking this action, and I have to determine, given state, what kind of action I should take in order to maximize my long-term reward. So I don't have time to go through the mathematics, but essentially it boils down to the so-called Bellman optimality equation. So the idea is, let's say the optimal actions represent a sequence of actions. If I say I have a sequence of actions which are optimal, then every subsequence of actions I'm taking must be also optimal. Okay, otherwise there's no way that I can get a sequence of actions to be optimal, and that is the Bellman optimality equation. And then you can actually define so-called the Q value, of a particular policy associated with each state and action pair. So essentially, this Q value reflects, given the current system state is S, and what's the value of taking action A according to this policy. And obviously, this value must be reflecting the long-term reward, weighted, exponentially weighted reward that we were talking about. So essentially is to find such policy, action policy, and so that we can maximize the long-term reward. And the problem is that we cannot solve if the problem is small, namely the combination of states and action pairs is small. Then you can solve it by table lookup, or you can solve it by tabular techniques. You essentially form a table and then you can sort it out. However, when the number of states is large and also number of action pair actions is also large, then you cannot solve. On the other hand, then we can introduce the concept of using a deep neural network. So essentially, the deep neural network is to serve as an approximation and to approximate the Q value given every single S and A, and W is actually the parameter, model parameter associated with the neural network. And then if we can train this neural network properly, then we get to the optimal Q values. From the Q value for different S and A pair, then we can identify what's the best action we should take for given state S. So in order to train, then we typically use this loss, define this loss function. Essentially, this is the L2 norm loss function people normally use to train your neural network. All right, with that, I would show one scenario, some numerical examples to illustrate the performance gain we can possibly get by reinforcement learning. What is shown here is some networks with some number of domains and also the corresponding parameter. What I shown here on the left-hand upper plot is horizontal axis is the training time as we go through the training. And then the vertical axis you can think of is actually the enhancement or the reduction of the latency for the path, for the routing path you select. Remember, we use routing path as an example. So the the bottom curve here, which is black, essentially this is a fixed frequency. That means I always come up with a fixed schedule. Domain 1 controller synchronized with 3, and then next time with 5. So you go through the periodic frequency. Every pair of the controllers will have the fixed frequency for synchronization. And then the light green one here essentially is the random. So you randomly pick, who you want to synchronize with. Okay, and then the learned, the reinforcement learning is the darker green performance. So you can see reinforcement learning indeed can gain a lot, because what the reinforcement learning is trying to learn from the observation of the reduction of your enhancement of your routing decision. Okay, and as we learn, then we will say, this domain is changing a lot in terms of status of the links and everything. So the synchronized controller with corresponding controllers will synchronize themselves more, update each others with their status more often. So that is the essence of the reinforcement learning. So you can see on setting after setting, we have significant performance gain by using reinforcement learning. Now, as I mentioned, reinforcement learning is a very powerful technique, but we do run into the state explosion, action explosion problem. And we have a set of techniques to address them. And I would like to, including this is called state action separable reinforcement learning. And there's some other techniques like state decomposition, hierarchical MDP, decentralized MDP, but I don't think I would have time. I would defer you to my website. You can go Google me, Google my name, go to Google Scholar. You would find my papers on a variety of issues. And here I would like to quickly mention about the state action separable reinforcement learning as a way to overcome the state explosion and action space issue. Okay, what's the essence of the technique? Basically, if you look at the traditional way to solve reinforcement learning problem, is to consider the current state of the system, and then you take certain action, and then you get some reward. Okay, and obviously what matters is to maximize your return, maximize your reward, based on the state and action pair. And that is where the explosion, there's so many combinations of state and action. So, but nevertheless, the idea is to have this so-called state action value function. What it means is that given certain state S, you take certain action, and that is the corresponding return or the value you have. That's what the actions, that's what you would like to optimize. And remember, it's the combination of S and A, the action, that causes us trouble. Then for a lot of problems, we observe that we don't really need to capture S and A simultaneously. What matters is what is the current state. Forget about your action at this moment. What's the next state? Now, give you an example. I have a minefield here on the right-hand side. So I have an agent. The agent is trying. There's some mines put on the ground in this minefield. So the agent is to make some decision how to move around. Okay, in this minefield. Hopefully, there's some exit door in the minefield. The agent would like to go to this exit without stepping on the mine. Okay, otherwise you blow up yourself. So what matters is, in this case, it's important to capture what's the current state, namely the current position of the agent, and what's the next position of the agent, regardless of what action you are taking, because the next position will tell you whether you step on a mine or not. So now you can see this is the the important part is what's the current state S, and what's the next state, next position of the agent, and then the action we can consider as an additional piece of information, but not as jointly as the way we jointly consider S and A together in the original formulation. So with that, so what we can develop is actually capture so-called the state, consider the current state and the next state, and then we come up with the reward. Okay, so we call this the state transition value function. Okay, and then so now we have the state S and S prime, and then we get the reward. So that tells us about how good the next state is, not the action that you take yet. Okay, however, to consider the action, we consider based on the state transition value function. Then we kind of be using supervised learning to remember actually when we have transitioned from S to S prime, because we know what action has been taken. So we learn another simpler supervised learning transition model to map the state transition from S to S prime to the corresponding action. Then we can have the complete picture. Okay, so you can see essentially we break the S and A combination to S to S prime, and then consider A. All right, so essentially you can come up with this new method. That's the reason why we call this state action separable. We separate the state transition from the action. And then using this method, you can see from here, there's some numerical assessment. So the performance of the new method comparing with some other existing method is the method is sitting at the represented by dark blue here, is much better than other existing method for different type of scenarios. So this method can perform fast, can learn faster, and then using less resources and require less memory. All right, I'm going to skip some other techniques which also help us to tackle the state explosion, action explosion problem. But I would like to highlight one ongoing work that we are talking about. Okay, and the idea here is we try to use reinforcement learning to control a very large system. Okay, let's say the large system is broken down into subsystems. You can call it domain. Okay, it doesn't really matter. So the big system consists of very large number of subsystems. You can think of each subsystem can be managed by one agent. Okay, you have multiple agents in this case. However, in order to support let's say the resource sharing across domain, the agents must work together. They cannot work just on their own because they have their requests. We have to make use of resources in other domains. So one possible solution is to have hierarchical reinforcement learning. Namely, we have another global agent sitting at the top. Each local agent would talk to the global agent to kind of synchronize and try to coordinate their action so that overall they work together in an optimal way. But then we also run into a problem is that the same state explosion problem still occur, because how much information the local agent have to tell the global agent? If we tell the same detailed information, then the global agent must have a very, very large space because of the Cartesian products of the state space. So we have to address the state space issues in this kind of hierarchical and distributed or multi-agent scenarios. This is ongoing research work. So it's very fascinating because in our world, we can't expect have a single agent to cover everything. Instead, we must have multiple agents due to various reasons. Maybe different domains belong to different owners. Different owners would like to have their own agents, reinforcement learning to control their own subsystems and subnetwork. So we can ask them to fit everybody into a single controller, and also a single centralized controller would not be agent would not be scalable anyway. So the problem of multi-agents, distributed agent for reinforcement learning is going to be there, and there are many issues remain open, waiting for us to work on. Okay, so I skipped this how to combine reinforcement learning with transfer learning when their environment is changed. And here's the list of publications. I think the best way is to, as I shown at the bottom here, just Google my name, and you can find my papers on my website. Okay, so this is what I have, and I hope I would have some time to answer your questions. Thank you very much for your attention.
Thank you so much, Professor Kin K. Leung, for that inspiring presentation on deep reinforcement learning for control of large-scale communication infrastructures. And we'll now move on to the question and answer segment, starting with this first question that we have here. And it is, as machine learning is so popular, how much does that represent a hype in the area of communication networks? And of course, the hype is in inverted commas. So yeah.
Thank you. Thank you. This is a very important question. I start to work on reinforcement learning in the last several years, and I to be honest, I start with a very skeptical mind. I didn't want to kind of jump onto the bandwagon just for the sake of working on something kind of hot. But from my own experience, I honestly can say reinforcement, in general, machine learning techniques can solve some problems which we didn't know how to solve, or it's not easy to solve in the past. So there's some very important value by using machine learning techniques in solving our problem. Having said that, as researchers, we have to be objective. We have to be honest, and telling colleagues, machine learning will be helpful in this way and that way. When we see some shortcoming, don't hesitate to tell people, hey, we have difficulty there also. But from my own experience, I can say it's very machine learning techniques in general, specifically for communication network management and control, is a new mine we can get into, and then you can take whatever you want. It's a gold mine. We can take whatever you want to do. The basic reason is, if you look at the reinforcement learning technique, essentially the state description is multidimensional. It can be huge dimension, okay, has very large dimension to describe the state. And what the machine learning technique is trying to explore the relationship between the state elements, of your state description, or in general, if you have a data item which is multidimensional, machine learning techniques can explore the relationship, very complicated relationship among the elements of your data, and this is really, really powerful. The relationship can be much sophisticated than any mathematics we can write down, including nonlinearity, including temporal characteristics of your data. So I think it has machine learning is not just a hype. Machine learning is something real, in my opinion.
Thank you so much, Prof, for that well elaborated answer. And we've got a couple more questions that just came in from our audience. This next question is, what are the key advantages of using machine learning techniques to manage communication networks over traditional approaches? What do you think the advantages could be?
Thank you. This is also a very important question. If you look at the traditional techniques we use for managing and control network, then we have, for example, we look at the control. We have control theory. We have optimization techniques, and those are very well established mathematical techniques we can apply to communication networks. There are a couple issues there. First of all, often let's say we focus on optimization, often we really need to have a good set of parameters. That means the network parameters must be, I'm talking about a communication network, I'm not talking about a neural network. The parameter you want to associate with the control of your communication network must be available. And those system parameters may not be accurately estimated, or they may change over time. So at this moment, this is how much traffic load you have, but it's not stationary. Maybe 1 hour later, now it's in Singapore, is about 5 o'clock. So your business hour is about to end. So you can see the traffic load on your internet is reduced. So there's non-stationarity of issue. So that means if you use a traditional way to do optimization-based management, then when the parameter changes, then you have to rerun your algorithm. You have to rerun your optimization again to get to the optimal setting you want to control. But if you use dynamic control, dynamic learning capability, then it's almost automatically, especially reinforcement learning. You can learn, you can adjust your parameters as time goes on. So it's a very dynamic environment. So that's one aspect. The other aspect is our mathematics have limitation. If you look at the optimization, we have convex optimization, non-convex optimization, but we have limited capability in writing down the relationship among the parameters. But for machine learning techniques, you don't need to write it down. There's some relationship we don't need to know. We don't know how to express mathematically, but it's somehow embedded, captured in your neural network. And that is perhaps enough from the application perspective. But of course, we would like to understand better the mathematical, have the mathematical understanding behind machine learning techniques. That is the challenge for the research community to work together. Okay, we are still, in many cases, machine learning techniques are still represented as a black box. It works, but we need to understand more than why it works, more than just working. We need to understand why it works, under what condition it would work, under what condition it would break, so that we can have a much more robust system design.
Thank you, Prof, for sharing your perspectives on that question. We have another question here, and this one is, how can we overcome the issue of not having suitable data sets to drive reinforcement learning for network management? How can we do it?
Well, this is also an important question. we often run into this kind of issue, namely lack of suitable data set to train. But fortunately, I would say the following. As far as the management and control of communication network is concerned, we don't have much difficulty in collecting appropriate measurements, data to drive our reinforcement learning algorithm. Of course, if we want to measure something, it requires some effort. It requires our system communication system designer to put some hooks, to take some measurements, to reflect. For example, if I take certain action, what's the performance gain I can get to reflect the reward? So those things need to be implemented. Otherwise, we cannot have enough measurements and data set to drive the reinforcement learning. So other than having those hooks in your system, in your networks, the rest is not that. Fundamentally challenging, I would say. It doesn't matter whether we can do it or not. And secondly, the measurements we are talking about is different from quantum physics. If you take the measurement, the state of the system changes. For our communication network, is still classical physical system. So measurements would not perturbate our system state. So in that sense, it's a relatively stable system. We can take some good measurements. Yes, indeed, system level measurements and observations will be needed, but no pain, no gain. If we don't measure enough, observe enough, then we won't be able to have good control, good management schemes developed for communication networks or for any other application as well. Thank you.
Thank you so much, Prof, for that very comprehensive answer to that last question. We have another question here that just came in, and it's this. Is there any data set regarding RIS features in wireless communication through the RL approach? Are there?
I think there. I think there are existing data set available for wireless. Of course, depends on what aspect of wireless you are talking about. And also, related to that is also not only wireless, but also for mobile communications, mobility. For example, some people capture mobility looking at how vehicles move around. Then there's some data set you can available to you. And also I understand that some operators, some service providers provide their data set regarding the traffic load of their base stations and their cellular network. So if you contact me by email, I should be able to point you to some of those. And also, you can search on the internet. So there are data sets available related to wireless network that you can use to drive your reinforcement learning.
Thank you so much, Professor Kin K. Leung, for helping to answer all those questions from our audience, and of course for that in-depth look into deep reinforcement learning for control of large-scale communication infrastructures. Now, once again, ladies and gentlemen, thank you so much for everyone's kind attention and participation throughout today. Of course, our gratitude as well to our sponsors and partners who have made this international workshop possible. A big thank you to the generous sponsorship of Anritsu Private Limited, Huawei International Private Limited, Keysight Technologies Singapore Private Limited, MediaTek Singapore Private Limited, MPix Innovations Private Limited, Quanta Computer Inc., Intel, Roder and Schwartz Asia Private Limited, ST Engineering, ST Microelectronics, and United Microelectronics Corporation. We'd also like to be giving our thanks to the support of the IEEE Communications Society and the International Electronics Manufacturing Initiative. Thank you very much to our sponsors and partners. Now, of course, there's more enlightening content tomorrow as we continue with 5 more speakers. And you can see them on screen right now. We have Professor Rafat Mansour with microwave and millimeter wave phase change material devices for future communications. We'll also be hearing from Professor Lin Chai with Toward Reliable and Scalable Vehicle to Everything. We'll also be having Professor Chan Byung Che with Biological Layer for 6G and B6G, Einstein, Reynolds, and Communications. We also have Professor Sun Su Mei with 5G to 6G, Driving Applications, Enabling Technologies, Research and Standardization. And finally, Dr. Alexander Chanakin, a new rubidium technology brings high stability and exceptional spectral purity. Truly looking forward to all of that, and we'll see you again tomorrow here at 9 a.m. Singapore time. See you tomorrow, everyone.